2 billion years ago, in what's now Gabon, a nuclear reactor switched itself on, ran for ages, then shut down without a single human hand. If the planet can accidentally build a machine that should never exist, it can erase one too. So are we really Earth's first technological intelligence, or just the latest survivors of a great filter that already wiped the others clean? The oldest crime scene on Earth isn't a ruin, it's a ledger of atoms, balanced and then disturbed. In stone that predates animals, the planet keeps accounts that can accuse nature, or implicate something else. After a discovery like that, certainty becomes a luxury, and geology becomes a witness with a broken memory. Earth looks ancient and stable from orbit, yet its surface is a restless draft. Continents drift, mountains rise, oceans open, and whole chapters are subducted into heat and pressure. Whatever once stood here is not simply buried, it is dissolved, recrystallized, and rewritten until it resembles ordinary rock. That is the unsettling premise of this film. If a technological species had appeared long before us, would we even recognize the evidence? Not statues or cities, but subtler signatures, ratios that refuse to behave, elements that arrive in the wrong proportions, layers that record a sudden pulse and then fall silent. We will follow the trail the way investigators do, by asking what must be true for a signal to survive deep time. What kinds of materials persist when iron rusts to dust and glass devitrifies into minerals? What happens to concrete under 100 million years of groundwater, or to plastics when heat and pressure turn them into carbon-rich ghosts? The planet has its own shredders, and they operate on a schedule that dwarfs human history. Plate tectonics consumes seafloor in a few hundred million years, sediments compact and trade chemistry with fluids. Metamorphism blurs textures until even sharp edges become rumours. The further back we look, the more the archive becomes selective, and the more absent stops meaning never happened. So the search changes shape. Instead of hunting for artifacts, we hunt for bookkeeping errors in nature's accounts, signals that are global, redundant, and difficult to counterfeit. Isotopes become our timestamps and our lie detectors, but they are also tricky witnesses because physics can mimic intention. That tension is the heartbeat of this story. A pattern can look engineered and still be accidental, while a genuine act of engineering can be ground down until it reads like background noise. To decide which is which, we need more than one clue. We need converging lines of evidence that survive skepticism, contamination, and the planet's endless remixing. And then there is the darker possibility hovering behind every measurement. Even if intelligence arises, it may not endure long enough to leave a loud signature. There may be filters, planetary gates that open only briefly, or catastrophes that thin complexity before it can stabilize. In the strata, extinctions can appear as a seam you could cover with your hand, yet they mark the collapse of worlds. We will examine how quickly life can be pushed past recovery, what a bottleneck looks like in chemistry and fossils, and how multiple stresses can stack until the system tips. But this is not a story told to flatter our imagination. It is a story told to test it, with instruments, baselines, and hard constraints. We will separate what is verified from what is merely suggestive, and we will keep returning to the same standard. Could nature do this? And if so, how? Because the most haunting outcome is not finding a forgotten empire. It is realizing how easily the planet erases ambition, and how narrow the window may be between first sparks and lasting fire. By the end, the question will feel less like a puzzle from the past and more like a pressure on the present. The next layer in Earth's record is forming right now, under our cities, in our oceans, and in the air we're changing. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We'll move from an authenticated anomaly to the mechanisms that destroy evidence, then to the forensic chemistry that can still catch deep-time imposters. Finally, we confront the Great Filter as both cosmic explanation and personal warning, and ask what trace we are writing into stone. A technician loads a uranium ore sample into a mass spectrometer, expecting a familiar fingerprint from a familiar element. The lab is quiet in the way clean rooms always are. Soft fans, muted footsteps, and the faint click of a sample tray locking into place. Inside the instrument, the routine is almost ceremonial. The sample is ionized, accelerated through electric fields, and bent by magnets that separate atoms by mass. On a monitor, peaks rise where isotopes should be, and the software overlays them against reference curves built from decades of measurements. The numbers return clean, repeatable, and wrong in a way that feels engineered rather than accidental. The peaks are sharp, the baseline is stable, and the statistical uncertainty is small. If this were a mistake, it would be a strangely disciplined one. Natural uranium should carry a stable ratio of isotopes, with U-238 dominating and U-235 as the small, predictable minority. In modern ore, U-235 sits near 0.7%, a fraction so consistent that fuel accountants treat it like a law. This sample shows U-235 missing beyond any reasonable measurement error, as if the ore has been burned. Not diluted by other minerals, not fractionated by a quirky chemical process, but selectively depleted in the fissile isotope. The signature resembles what you see after uranium has already done the work we build reactors to do. In nuclear terms, it looks used, like spent fuel pulled from a reactor core after years of fission. Spent fuel is not simply less radioactive, as people sometimes assume. It is chemically transformed, crowded with daughter products and altered isotope ratios. The defining feature is that U-235 has been consumed, because it is the isotope that most readily fissions with slow neutrons. The lab repeats the run, checks calibration standards, and swaps instruments to rule out drift. They verify mass bias corrections, they inspect blanks for contamination, and they compare against certified reference materials. When the same depletion appears again, the room's mood shifts from troubleshooting to disbelief. The depletion remains, and the anomaly spreads across multiple samples from the same source. If the data are real, then something in the ground once consumed U-235, not in a single flash, but in a sustained process that left a measurable scar. That implication is the hook, and it is not a myth or a fringe claim. It is a verified discovery from the 1970s, tied to a place called Oklo in Gabon. The name sounds like a footnote, yet it points to one of the strangest confirmed events in Earth's deep history. Oklo is not a single site, but a cluster of reactor zones embedded in ancient uranium-bearing rock. The landscape today is green and humid, with laterite soils and dense vegetation masking the older geology beneath. Under that surface lies a record written in isotopes, preserved like ink pressed into mineral grains. Researchers eventually identified more than a dozen distinct zones where fission occurred. These zones are not identical, and they are not neatly arranged like engineered fuel assemblies. They appear as lenses and seams of ore within sandstone and clay-rich layers, shaped by groundwater, sedimentation, and time. The discovery began with routine accounting, because nuclear fuel programs track isotopes with obsessive precision. In the era of expanding nuclear power, every shipment of uranium was measured, logged, and reconciled, because small discrepancies can signal diversion or error. The system is designed to notice even tiny departures from expected composition. When French analysts noticed unusual U-235 depletion in ore shipments, the trail led back to Gabon. The ore came from a mine feeding the French nuclear industry, and the anomaly was not subtle. It was large enough to matter economically, and strange enough to demand an explanation. Geologists and nuclear chemists then asked a blunt question that sounded impossible. Could a natural deposit have reached criticality and sustained a chain reaction? The idea collided with intuition because we associate reactors with control rods, containment vessels, and deliberate design. The answer emerged from isotopic ratios that do not lie easily. Alongside missing U-235, the ore carried fission products with patterns matching reactor physics. Those products were not random contaminants, and they were not the result of ordinary radioactive decay. Neodymium isotopes were a key clue, because neodymium has multiple stable isotopes produced in characteristic fission yields. When uranium fissions, it tends to split into mid-mass fragments, and certain neodymium isotopes appear in predictable proportions. In Oklo samples, those proportions matched what you expect when uranium nuclei split repeatedly over long periods. The neodymium story is persuasive because it behaves like a ledger. Different fission pathways produce different isotope balances, and those balances are difficult to fake through chemistry alone. If the neodymium ratios line up with known yield curves, then the simplest explanation is that fission actually happened. Other fission signatures appeared in xenon trapped in minerals and in the distribution of rare earth elements. Xenon is a noble gas, and noble gases do not readily bond, so their presence and isotopic makeup can preserve a snapshot of nuclear events. In Oklo, xenon isotopes looked like the breath of a reactor, caught and sealed inside crystalline cages. The evidence pointed to controlled fission, not a one-time explosion. There was no crater, no shock metamorphism, and no global layer of fallout. Instead, there was a localized, sustained conversion of uranium into daughter products, moderated by conditions that kept the reaction from running away. Oklo forces us to separate two ideas that often blur together. Something can look technological and still be natural, if the physics allows it. The universe does not reserve complexity for engineers, and geology has had billions of years to explore combinations we rarely imagine. To understand why Oklo worked, we need a minimal reactor vocabulary. A fission chain reaction depends on neutrons, and on whether each fission event triggers at least one more. When a U-235 nucleus splits, it releases energy and additional neutrons, and those neutrons are the currency of continuation. Criticality is the threshold where the neutron economy balances, so the reaction sustains itself. Below critical, the chain dies out, and above it, power rises until feedback slows it. In practical terms, criticality is about probabilities. How many neutrons are lost to absorption, leakage, or capture without fission? In engineered reactors, moderators slow neutrons to increase the chance they cause new fissions in U-235. Fast neutrons are energetic, and U-235 can fission with them, but it fissions much more readily with slow, thermal neutrons. Water is a common moderator because hydrogen nuclei are similar in mass to neutrons and can slow them efficiently through collisions. Oklo had the same ingredients, arranged by geology instead of design. It had concentrated uranium ore, it had groundwater, and it had rock that could confine the geometry. The ore bodies were thick enough and continuous enough that neutrons could bounce around rather than escape into surrounding rock. Geometry matters because neutrons are impatient travelers. If too many leak away, the chain reaction cannot sustain itself, even with plenty of fuel. In a reactor zone, the shape and the surrounding materials act like a boundary condition, quietly deciding whether criticality is possible. The most surprising ingredient is time, because isotope ratios change across billions of years. 2 billion years ago, natural uranium contained a higher fraction of U-235 than it does today. This is not a speculative claim, but a consequence of half-lives, the slow arithmetic of radioactive decay. U-235 decays faster than U-238, so the farther back you go, the richer natural uranium becomes in the fissile isotope. U-235's half-life is about 704 million years, while U-238's is about 4.5 billion years, so their proportions drift steadily. At Oklo's age, the U-235 fraction was roughly a few percent, closer to what modern reactors can use with moderation. That higher fraction meant a deposit could cross the critical threshold with help from water moderation. In today's world, the same deposit would likely fall short. The Earth did not change its laws, but it did change its starting conditions, so the basic picture is simple, even if the details are complex. Water seeps into uranium-rich rock, slows neutrons, and a chain reaction begins. The first moments would not look like science fiction, because the power levels were modest, yet the physics would be unmistakable. Then physics adds a self-regulating twist that makes the story feel almost designed. As the reaction heats the water boils away or is displaced. In effect, the moderator removes itself when the system gets too hot, turning down the reaction without any human-built control rods. With less water, moderation drops, neutrons stay fast and the reaction slows or stops. When the rock cools, water returns, and the cycle can restart. This is a feedback loop, and feedback loops are the hidden architecture of many natural systems. Researchers infer this pulsing behavior from modeling and from the distribution of reaction products, the spacing of altered mineral zones, the thermal history recorded in surrounding rock, and the inferred movement of fluids all point to intermittent operation. Oklo likely ran in cycles, with on and off periods governed by heat, permeability, and groundwater flow. It is worth pausing on what intermittent means here, because our instincts are tuned to human time. A cycle could be hours long or days long, repeating like a slow heartbeat in stone. Over thousands of years, those pulses would accumulate into a total burn-up that matches the isotopic evidence. This is where the timescale becomes the real shock. These were not brief events, but long-lived natural reactors operating over hundreds of thousands of years. Not a single lucky moment, but a stable arrangement that persisted through climate shifts, sediment compaction, and the ordinary churn of Earth's surface. Power estimates vary by zone and by model, but they converge on modest outputs by industrial standards. Many zones likely produced on the order of tens of kilowatts, with peaks near about 100 kilowatts. That is the scale of a small building's electrical load, except here it was heat released inside rock. That is enough to matter chemically and thermally, but not enough to melt a continent. It is a slow burn, sustained by geology and moderated by water. The surrounding minerals would have been warmed, altered, and subtly reorganized, like a kiln that never quite reaches the temperature of catastrophe. Even modest power becomes significant when it lasts. Over long spans, the total energy released is enormous, and the cumulative fission count becomes a measurable geological event. The rock remembers, not as a dramatic scar, but as a quiet rebalancing of isotopes. The reactors also did something else that matters for our larger question. They stored their own waste, because many fission products remain trapped in minerals for immense spans of time. In an engineered reactor, waste is removed and managed, but at Oklo the waste had nowhere to go except into the surrounding geology. Oklo became a natural experiment in containment, showing how radionuclides can migrate or stay put in real rock. Some products moved with fluids, and many remained remarkably localized. The details depend on mineral chemistry, redox conditions, and the microscopic pathways that water can exploit. This containment is not perfect, and it is not uniform, but it is informative. It tells us what geology preserves and what it smears into noise. It also tells us that forever is not a single condition, but a negotiation between rock, water, and time. If you stand at the site in your imagination, the visuals are almost paradoxical. There is no glowing core, no humming turbine hall, and no warning sirens, only layered rock and the slow drip of groundwater. Yet the isotopes insist that a reactor once lived here, cycling in darkness long before mammals existed. That brings us to the method of this documentary, because mysteries in deep time invite careless leaps. We will follow evidence first, and we will label speculation as speculation. The goal is not to drain wonder from the story, but to keep wonder tethered to what can be tested. Confirmed facts are measurements that independent teams can reproduce, anchored to known physics and geochemistry. At Oklo, the isotopic depletion and fission product signatures meet that standard. They appear in multiple labs using different instruments, and they cohere with nuclear data measured in controlled settings. Interpretations are the models that explain those facts, and models can change as new constraints appear. Oklo's natural criticality is now the consensus interpretation because it fits the data best. It explains the missing U-235, the neodymium patterns, the xenon isotopes, and the localized nature of the event in one framework. Speculation begins when we extend beyond what the rock can actually tell us. Deep time is not a friendly archive, and it destroys as much as it preserves. The past is not a library with intact shelves, but a landscape where pages are torn out, rewritten, and sometimes burned. Erosion removes surfaces, tectonics recycles crust, and metamorphism resets chemical records. Even without dramatic events, groundwater and heat can blur sharp signatures. A signal that looks crisp today may have survived only because it was sheltered, mineralized, and lucky. So absence of evidence is not evidence of absence, especially across billions of years. Yet we also cannot treat every gap as proof of hidden civilizations. The discipline is to hold both truths at once, and to resist using uncertainty as a blank check. Our rule is simple and demanding. A claim about ancient technology must survive the same scrutiny as Oklo's reactor claim, with multiple lines of hard evidence. It must show patterns that are difficult for natural processes to mimic, and it must be consistent across independent measurements. Oklo matters because it sits at the boundary between the natural and the artificial in our intuition. A reactor feels like an artifact, yet here it is as a geologic phenomenon. This site teaches a humbling lesson. Our category labels are not laws of nature. That tension reframes the central question of this series. Are humans Earth's first technologically capable intelligence, or have others arisen and vanished before us? The question is not asked as a promise of sensational answers, but as a test of what the planet can remember. The Great Filter hypothesis suggests that many paths to advanced civilization end in failure, leaving few survivors to spread and endure. If filters operate on cosmic scales, they could also operate on Earth. Extinction, collapse, and the slow erasure of evidence are all filters of a different kind. Oklo does not prove an earlier civilization, and it does not need to. It proves something more useful for our investigation, which is that nature can mimic our most advanced signatures. A phenomenon can look like engineering, because the underlying physics is the same physics engineers exploit. If a nuclear reactor can happen without engineers, then some apparent artifacts might be misread geology. But the reverse is also possible because geology can erase engineers until only chemistry remains. When structures crumble and metals corrode, isotopes may be the last durable testimony. This is the pivot point for Chapter 1, and it sets the stakes for everything that follows. We are searching for signatures that could survive deep time, and for tests that can falsify them. The emphasis is on survivability, because the Earth is an active planet that edits its own past. We will ask what kinds of technology leave persistent isotopic scars, unusual minerals, or global chemical shifts. We will also ask what natural processes can counterfeit those same signals. The challenge is not merely to find anomalies, but to separate meaningful anomalies from the planet's ordinary strangeness. Oklo gives us a calibration point, a real anomaly that became understandable without losing its strangeness. It tells us to respect the data and to distrust our first story. It also reminds us that the most unsettling discoveries can begin as a routine spreadsheet discrepancy. From here, the question widens beyond one mine in Gabon. If Earth can build a reactor and hide it in plain sight, what other deep-time signatures might we be missing or misnaming? What else might sit in museum drawers and core samples, waiting for the right measurement to make it speak? Next, we follow the trail from one impossible measurement to a broader forensic toolkit. We move from reactors to the planet's long memory, and to the places where that memory breaks. And as we do, we keep Oklo in view, a reminder that the impossible sometimes arrives as a clean, repeatable number. Oklo leaves us with a disciplined kind of unease, the kind that settles in after the facts are checked twice. The reactor is real, the isotopes are real, and the event is natural, yet it behaves like something designed. That combination forces a harder question than the obvious one, because it shifts our suspicion from the artifact to the planet. If Earth can produce something that looks engineered, Earth can also erase engineering until it looks natural. The central question stays the same, and it does not soften with repetition. Are humans Earth's first technologically capable intelligence, or did others rise and vanish in deep time? Chapter 1 gave us a calibration point, a case where improbability turned out to be geology. Chapter 2 explains why the search for older technology is not a treasure hunt with a lucky shovel. It is a preservation problem, one governed by physics, chemistry, and the slow violence of time. Earth is not a static museum with locked display cases and polite lighting. Earth is an active planet that recycles its own evidence, and it does so without malice or intention. The surface is a worksite where heat, water, and gravity keep editing the record. Over millions of years, landscapes are planned down until their sharp edges become rounded arguments. Over hundreds of millions, entire ocean floors are replaced, as if the planet periodically clears its desk. Plate tectonics is the first shredder, and it works at continental scale. The crust is broken into moving plates that collide, split, and dive, driven by mantle convection and the planet's internal heat. At subduction zones, oceanic crust sinks back into the mantle, and the process is not gentle. Whatever was built on that seafloor is not buried like a time capsule in dry sand. It is heated, squeezed, hydrated, and transformed until it becomes new rock, then new magma, then something else entirely. If we could watch that boundary in accelerated time, it would look like a slow conveyor belt feeding the deep earth. A trench opens like a wound in the ocean surface, and sediments slide toward it in quiet avalanches. The descending slab drags water-rich minerals down with it, and those minerals release fluids under pressure. Those fluids change melting points and trigger volcanism. So the recycling is not just burial, it is chemical reprocessing, with the mantle acting like a furnace that does not keep receipts. The timescale is not vague, and it is not forgiving. Most oceanic crust is recycled in roughly 200 million years, a number constrained by seafloor spreading rates and the age distribution of ocean basins. That is shorter than the age of the dinosaurs, and it is a blink compared to the billion-year spans where earlier civilizations would have to hide. If a coastline hosted cities for 1 million years, the seafloor that received their debris could still be gone. Even their land-derived sediments might be scraped off, folded, or cooked into metamorphic rock before anyone could recognize them. The ocean is especially cruel to permanence because it is where so much ends up. Rivers deliver the planet's weathered skin to continental shelves, and shelves are temporary ledges. When sea level drops, rivers cut down and move sediment farther out. When sea level rises, waves rework the same material again, sorting grains like a patient machine. Then tectonics tilts the shelf and gravity finishes the job, sending everything toward deep basins that may later be subducted. Continents feel more permanent, and on a human map they look like fixed stages, but they are not safe, because they are not still. Mountains rise where plates collide, and their height is a promise that erosion will come. Rivers grind rock into sediment and carry it to basins, measuring time in grains. Wind and ice do the same work in different climates, with glaciers acting like bulldozers that scrape bedrock clean. The result is not preservation, and it is not even orderly loss. The result is redistribution, where the same atoms are moved, mixed, and relabeled. Erosion is not just the wearing down of peaks, but the systematic removal of context. A carved stone can survive, but the layer that told you where it belonged can be stripped away. A building can collapse, but the rubble can be carried downstream and scattered across a floodplain. Over long spans, landscapes do not merely decay, they are disassembled and reassembled elsewhere, and the reassembly rarely preserves the original story. Sedimentation is a second shredder that looks like storage, which is why it can mislead our intuition. Layers accumulate and bury what came before, and burial feels like protection. Yet burial brings pressure, heat, and fluids, and those are agents of change. Sediments compact, cement, and often metamorphose as they are pushed deeper, and the process is slow enough to seem invisible. The original textures blur, pores collapse, and the chemistry re-equilibrates with circulating groundwater. A ruin becomes a mineralized smear, then a rock that no longer advertises its origin. In a cross-section of a sedimentary basin, the story is written as stripes. But the stripes are not static. Clay minerals transform, organic matter matures, and dissolved ions migrate along tiny pathways. If an artifact is buried, it becomes part of that chemical conversation, exchanging atoms with its surroundings. Even when a shape survives for a while, its edges are softened by dissolution and pressure solution. The basin keeps a record, but it is a record of conditions, not intentions. Metamorphism is the third shredder, and it is ruthless because it targets structure itself. When rocks are heated and compressed, minerals recrystallize into new forms that are stable at higher temperature and pressure. Isotopes can diffuse, and chemical gradients can flatten, especially when fluids are present. The rock keeps a memory, but it is a rewritten memory, translated into the language of mineral assemblages. It records temperature and pressure more clearly than it records architecture, and it can erase the difference between natural and artificial textures. Even without metamorphism, time attacks artifacts through ordinary chemistry, and ordinary is enough. Metals oxidize and dissolve, and the products are often more stable than the original metal. Concrete reacts with water and carbon dioxide, slowly changing its mineralogy and weakening its structure. Plastics fracture, then become microfragments, then become carbon in soils and sediments, and the transformation is accelerated by heat and microbes. The longer the timescale, the more the planet turns objects back into cycles, as if insisting that nothing stays outside its bookkeeping. This is why the scarcity of ancient rocks matters, and why it is not just a trivia fact. Most exposed crust on Earth is younger than 1 billion years, a consequence of continuous recycling and resurfacing. Older rocks exist, but they are rare at the surface, and their rarity is itself a message. They are often buried, altered, or broken into isolated windows where erosion has cut deep enough to reveal them. The farther back we look, the fewer pages remain, and the pages we do have been edited. There is a historical irony here, because geology itself was built on the realization of deep time. Early geologists learned to read strata as sequences, and they learned that Earth's history is vast beyond ordinary imagination. Yet the same deep time that makes ancient civilizations conceivable also makes them difficult to verify. The planet is old enough for many experiments, but old enough to clean up after them. The exceptions are cratons, the oldest stable cores of continents, and they matter because they resist the fastest forms of recycling. Cratons are thick, buoyant, and mechanically strong, which helps them avoid deep subduction for long spans. Their roots can extend hundreds of kilometers into the mantle, acting like keels that stabilize them. They are not immune to erosion, but they avoid the most complete forms of tectonic destruction. They act like partial archives, not complete libraries, and the difference is crucial. These archives are unevenly distributed, and on a world map they appear as scattered strongholds of antiquity. Parts of Canada, Australia, and southern Africa hold some of the oldest exposed rocks, including ancient granites, greenstone belts, and high-grade metamorphic complexes. Some contain sediments that once sat on very old surfaces, preserving weathering profiles and ancient river deposits. If deep time technology left anything durable, cratons are where we would expect hints, because they offer the longest uninterrupted custody. Yet even cratons are not simple time capsules, and their stability can be overstated. They have been heated, intruded, and deformed across multiple events, including continental collisions that stitched supercontinents together. Their sediments have been uplifted and eroded, then reburied in later basins, sometimes more than once. Their groundwater has moved elements through fractures for hundreds of millions of years, quietly altering chemistry. An archive can preserve a signal while still distorting it, like a document that survives but has been smudged. So we need to be explicit about what we mean by evidence, because our instincts are tuned to short timescales. A stone tool seems durable on human timescales, and in the right cave it can survive astonishingly long. Over 1 million years it might persist in a dry basin, a lava tube, or a protected sediment layer. Over hundreds of millions it is likely ground down, buried, or metamorphosed, losing the sharpness that makes it legible. Over 1 billion years, even stone becomes part of a new rock cycle, and the tool becomes merely a grain among grains. Metals feel more diagnostic because they imply smelting, refining, and industry, which are hard to confuse with simple biology. Yet metals are chemically eager to react, and their reactivity is a kind of built-in self-erasure. Iron rusts and hydrates, copper weathers into carbonates and sulfides, and aluminum forms oxides that quickly pass as ordinary minerals. Under heat, alloys can separate, and under pressure they can deform until their microstructures are no longer distinctive. In sediments, metals can dissolve and reprecipitate as sulfides or oxides, and the element remains as ordinary mineral grains. The artifact disappears, and what is left looks like geology doing geology. Plastics are often framed as immortal, but deep time is not a landfill, and chemistry is relentless. Sunlight and oxygen break polymers quickly at the surface through photodegradation and oxidation, turning strong materials into brittle fragments. Burial slows that breakdown, but pressure and temperature eventually change the chemistry, and microbes can exploit weakened bonds. Plastics can become waxy residues, then carbon-rich films, then indistinguishable organic matter, especially after heating during burial. A polymer signature might persist for a while, but it is not a billion-year monument, and it may not remain recognizable. Glass and ceramics can last longer in some environments, which is why archaeologists prize them in human ruins. They can also devitrify, crack, and dissolve in groundwater, especially when water is slightly acidic or rich in dissolved ions. Volcanic glass shows how quickly amorphous materials can alter, turning into clays and zeolites over surprisingly short geological intervals. Even when fragments survive, they become mixed into sediments and reworked by rivers and waves. A future geologist might find grains, but not a city, and not the story that made the grains meaningful. The uncomfortable conclusion is that ruins are the least reliable evidence, even though they are what our imaginations reach for first. Buildings are surface features, and surfaces are temporary because they are where energy flows most freely. The more time passes, the more the planet prefers chemistry over shapes, and the more it rewards what can hide in crystals. If an ancient civilization existed, the most likely survivors are not statues. The survivors are subtle shifts in minerals and isotopes, the kind of evidence that does not look like evidence until you measure it. That brings us to technosignatures, the forensic category we actually need. A technosignature is any measurable trace of technology that persists beyond the society itself, even after its objects are gone. In astronomy, it can mean radio signals, waste heat, or atmospheric pollutants on exoplanets, all inferred at a distance. On Earth, it means something that survives geology long enough to be found in rock, ice, or sediment. The question becomes which signatures are robust against the shredder, and which are illusions created by natural processes. We can group techno-signatures into 4 categories, not as rigid boxes but as practical search modes. Chemical signatures include industrial pollutants and unusual isotope ratios, especially when they appear abruptly. Physical signatures include mining scars and engineered materials, the things you might photograph from a drone. Biological signatures include abrupt ecosystem shifts and novel compounds moving through food webs, recorded in fossils and biomarkers. Energetic signatures include radiation products and long-lived nuclear isotopes, the fingerprints of high-energy processes. Chemical signatures are often the most durable because they can be locked into minerals, and minerals can persist when shapes cannot. Industrial activity can change the ratios of stable isotopes in carbon, nitrogen, sulfur, and metals, and those ratios can be measured long after the source is gone. It can concentrate rare elements in unusual combinations, creating geochemical patterns that stand out against natural baselines. It can produce synthetic molecules that later break down into distinctive residues, leaving behind unusual distributions of carbon chains or halogens. Even when objects vanish, altered chemistry can remain, because chemistry is the part that gets archived. Isotopes are especially powerful because they behave like accounting records, and they are hard to fake in detail. Natural processes fractionate isotopes in characteristic ways, because lighter isotopes move and react slightly differently than heavier ones. Biology prefers lighter carbon, so organic matter tends to be depleted in carbon-13 relative to carbon-12. Evaporation prefers lighter water, so rainfall and ice carry distinctive hydrogen and oxygen isotope patterns. Industrial processes can create different patterns, including sharp anomalies that do not match known natural pathways, and the sharpness matters. If we are looking for deep time industry, we are looking for isotope math, numbers that refuse to fit the usual equations. Physical signatures are the most intuitive and usually the least persistent, which makes them emotionally satisfying but scientifically fragile. Mining moves enormous volumes of rock and leaves scars, and on modern Earth those scars can be seen from space. Quarries, tailings, and tunnels can last for thousands of years, and sometimes longer in erode regions. Over millions, erosion fills them, and vegetation erases them, and the scars become subtle topography. Over hundreds of millions, tectonics can fold them, bury them, or metamorphose them, turning a mine into a distorted layer that looks like any other disturbed rock. Megastructures sound like the ultimate proof, but they face the same physics, and physics is indifferent to ambition. A dam becomes sediment as reservoirs fill and spillways fail, and the river resumes its work. A highway becomes gravel, then becomes a line of slightly different stones mixed into a soil profile. A city becomes a layer of rubble, then a soil horizon, then a lithified bed that might be only centimeters thick. The larger the structure, the more it interacts with rivers, coastlines, and faults, and those interactions accelerate its destruction. Size does not guarantee survival when the surface is temporary, and when the surface is where water and oxygen operate. Biological signatures are indirect but potentially global, which makes them tempting as markers. A technological species can drive extinctions, spread invasive organisms, and alter nutrient cycles through agriculture and habitat engineering. It can shift the balance of carbon burial and oxygen production, changing what gets locked away in sediments. It can leave a spike in charcoal from widespread burning, visible as dark layers or microscopic soot. It can create a sudden change in pollen, spores, or microfossil assemblages as landscapes are simplified and then repopulated. Yet biology is also noisy, and the noise is not a small complication. Mass extinctions happen without technology, and they can be triggered by impacts, flood basalts, or climate feedbacks. Climate swings reorganize ecosystems repeatedly, and the fossil record is full of abrupt transitions that have no intelligent cause. Volcanism can produce global stress and ocean anoxia, leaving chemical and biological signals that mimic industrial disruption. A biological signature can suggest disturbance, but it rarely points to intelligence by itself. It needs to align with other lines of evidence, and it needs to resist natural explanations. Energetic signatures include the most dramatic possibility, and they also carry the most risk of misinterpretation. Nuclear technology can create long-lived isotopes and fission products, some with half-lives that span millions of years. A global layer enriched in certain radionuclides could be suggestive, especially if accompanied by unusual isotopic ratios of xenon, neodymium, or uranium. But Oklo teaches caution, because nature can also run nuclear chemistry under the right conditions, and it can do so without any machinery. The lesson is not that nuclear signatures are useless, but that they require context and careful discrimination. Oklo also teaches a second lesson, one that's easy to miss if we focus only on the headline. The strongest evidence may be local and mineral-bound, not global and obvious, because local conditions control what gets trapped. Fission products were trapped in specific minerals and zones, held in place by crystal structures and geochemical barriers. A civilization's energetic signature could be similarly patchy, concentrated where waste was stored or where reactors operated. It might sit in a basin, a landfill, or a mine, then be scattered by later geology. The signal could survive, but only as a difficult measurement, the kind that looks like a lab anomaly until it repeats. Here is the key tension that shapes the entire investigation, and it is not comfortable. The more advanced a civilization becomes, the more it can alter global cycles, because energy use scales with industrial reach. It can change atmospheric composition, ocean chemistry, and sediment fluxes, leaving a planetary footprint. Yet those very alterations can become subtle in the long run, because the Earth system mixes and buffers disturbances. They blend into background geology as numbers, not monuments, and numbers are easy to overlook without a hypothesis. A primitive society might leave stone tools that are recognizable for a while, especially if they are concentrated in protected sites. An industrial society might leave fewer durable objects because it relies on complex materials that corrode and disperse into the environment. Its most persistent footprint could be a thin layer of altered sediments, enriched in metals or combustion residues. It could be a carbon isotope excursion from fossil fuel burning, where ancient carbon floods the atmosphere and shifts ratios. It could be a spike in heavy metals from mining and smelting, locked into clays and sulfides and carried into marine muds. That is counterintuitive, and it matters for how we search, because it reverses the usual logic of discovery. We are trained to imagine lost cities and buried pyramids, because those are the stories that survive in human memory. Deep time does not reward that imagination, because deep time is not a landscape of ruins. Deep time rewards boring samples, careful baselines, and statistical confidence, the slow accumulation of evidence rather than a single dramatic find. The evidence, if it exists, will look like geochemistry before it looks like archaeology, and it may never look like archaeology at all. This is where the Silurian-style question enters, not as a claim, but as a stress test for our assumptions. Could an industrial civilization have existed tens or hundreds of millions of years ago and be nearly invisible today? Not because it left nothing, but because Earth processed what it left, grinding it down and mixing it in. The question forces us to separate what we want to find from what could realistically survive, and it forces us to admit how much of the past is missing. Imagine a civilization that industrializes, burns carbon, mines metals, and synthesizes chemicals, and imagine it doing so with competence. It might operate for 10,000 years or 1,000,000, then collapse through war, climate, or simple exhaustion of resources. Its cities would be coastal because trade and food favor coasts, and because rivers and harbors make logistics easier. Its waste would concentrate in basins and deltas, where water carries everything downhill and deposits it in quiet layers. Those are exactly the places most likely to be subducted, flooded, or reworked, because they sit at the edges of continents where tectonics and sea level are most active. Even if some artifacts were buried quickly, the long-term odds are harsh, because burial is only the first chapter. Rivers migrate and cut new channels, slicing through old deposits and redepositing them elsewhere. Sea levels rise and fall, reworking shelves repeatedly and turning once stable ground into surf zone. Glaciations scour continents, stripping soils and pushing debris into new basins, and the scoured surfaces reset the clock on preservation. Later civilizations, including ours, would build on the same favourable terrain and destroy older deposits, because the best places stay the best places. The record becomes a palimpsest of occupation and erasure, written and rewritten on the same fragile paper. Now stretch the clock to hundreds of millions of years, and the map itself becomes unrecognisable. Continents rearrange and mountain belts rise where oceans once were, turning marine sediments into high plateaus. Sedimentary basins are uplifted and eroded, exposing layers that were once kilometres deep. Heat from burial alters organic molecules and resets some isotopic systems, especially those sensitive to temperature and fluid flow. What remains is a thin probability distribution of survivals, not a coherent ruin field, and the surviving pieces may be scattered across different continents. Stretch again to billions of years, and the problem becomes almost absolute, because repetition compounds. Plate tectonics has had time to recycle most surfaces multiple times, and each cycle is another pass through the shredder. Even stable cratons have been weathered and reworked, their sediments stripped and their surfaces renewed. The biosphere itself has changed, altering how carbon and oxygen move through the system, and those changes alter what gets preserved. 1 billion years is enough time for almost any physical artifact to become ordinary rock, and for its context to be erased. So the question is not whether evidence could survive at all, because in a large enough planet some traces always do. The question is what kind of evidence is most resistant to being averaged away by mixing, metamorphism, and time. The best candidates are those that become part of mineral lattices or global sedimentary patterns, because lattices and patterns can outlast shapes. They are signals that can be measured even after the objects are gone, and measured repeatedly in different places. They are the kind of traces that survive as chemistry, not as sculpture. This reframes our approach to the great filter on Earth, and it adds a darker possibility. If earlier technological species existed, the filter might not only be extinction, where a society ends and leaves ruins behind. The filter might also be epistemic, where the planet erases their obvious traces so completely that later species cannot prove they were here. Deep time becomes a second kind of silence, not because nothing happened, but because the record cannot speak clearly. But silence is not the same as emptiness, and Oklo is our reminder of that distinction. Oklo is a reminder that the ground can hold improbable histories, sealed inside minerals that do not advertise what they contain. It also shows that the evidence may be hiding in plain sight, inside ratios that look slightly wrong until someone asks the right question. The past can be present without being visible, and the difference between visible and measurable is the difference between myth and science. From here, the investigation shifts away from the artifact hunt, because the artifact hunt is optimized for the wrong timescale. We stop expecting intact machines and recognizable skylines, because those are surface fantasies in a world that recycles surfaces. We start asking what sediments remember when everything else forgets, and we start treating the planet like a statistical archive. If deep time has a shredder, chemistry is the bin where the shreds collect, mixed, compressed, and preserved as numbers. Next, we follow that bin, and we do it with caution rather than certainty. We look for isotopes, pollutants, and stratigraphic spikes that could mark industry, and we ask what baseline they should be compared against. We also ask how nature can counterfeit those same markers, and how to tell the difference when the signals are faint. The mystery does not get easier, but it becomes testable, and testable mysteries are the ones science can live with. And the central question sharpens again, because the stakes are not only historical. If we are not the first, the evidence may already be under our feet, embedded in rocks we have walked over without noticing. It may be thin, disputed, and easy to misread, because deep time turns clarity into ambiguity. The only way forward is to learn the planet's editing rules, then search for the edits that look intentional, edits that refuse to blend into the background. Oklo taught us a hard lesson in humility, because a reactor signature can be real and still be natural. In the rocks of Gabon, the planet quietly demonstrated that physics does not need engineers. The implication is unsettling and clarifying at once. If we want to recognize lost worlds, we must first learn how Earth can imitate them. So Chapter 3 becomes a detective story, but the clues are not ruins or machines. The clues are ratios locked inside minerals, waiting for measurement under clean lights and careful protocols. Imagine a core sample split open like a book, each grain a sentence written in atomic ink. What looks like ordinary stone can carry a ledger of neutron captures, decay chains, and chemical sorting. Forensic geochemistry starts with a simple idea, and it is almost too small to feel consequential. Atoms of the same element can have different masses, even when their chemistry looks nearly identical. Those variants are isotopes, defined by neutron count in the nucleus. Protons give an element its name, but neutrons quietly adjust its weight and its stability. Chemistry mostly treats isotopes alike because electrons control bonding and reactions. Yet physics and biology do not treat them equally, because mass influences motion, vibration, and nuclear behavior. A heavier isotope diffuses more slowly through a crystal lattice, and it can shift reaction rates in subtle, measurable ways. In living systems, enzymes often prefer lighter isotopes, and that preference becomes a fingerprint. Some isotopes are stable and persist indefinitely, which makes them reliable tracers across deep time. Others are radioactive and decay on predictable schedules, releasing particles and energy as they transform. That transformation is not random in its statistics, even if any single atom decays unpredictably. Over large populations, decay behaves like a clock. Half-life is the clock that matters, and it is both simple and profound. It is the time for half a population of atoms to transform into something else. After one half-life, half remain. After two, a quarter remain, and the curve continues downward. This is why radioactivity can date rocks, but it can also diagnose unusual histories. Radioactive decay produces daughter products, which are the chemical heirs of a parent isotope. The parent disappears while the daughters accumulate, creating a lineage that can be reconstructed later. In principle, it resembles genealogy, except the family tree is written in nuclei rather than names. When the system stays closed, the math becomes remarkably strict. In deep time, absolute amounts are rarely the cleanest evidence, because Earth is a master of rearrangement. Water moves through pores, melts migrate, and minerals dissolve and reprecipitate, redistributing elements. Ratios are harder to erase because mixing often preserves proportional relationships, even when concentrations change. A diluted signal can still be diagnostic if its proportions remain coherent. Scientists measure isotope ratios with mass spectrometers, instruments that turn matter into ions and then sort them by mass. The sample is dissolved or ablated, ionized in a plasma or by a filament, and guided through electromagnetic fields. Peaks rise on a screen like a skyline, each one representing an isotope counted by a detector. Calibrated standards anchor the measurement, so a ratio in one lab can be compared to a ratio in another. Every measurement begins with a baseline, because you cannot call something anomalous without knowing what is normal. You need to know what Earth normally produces before you call something out of place. Baselines come from average crustal compositions, from well-characterized reference materials, and from regional geology. Even then, normal is not a single number. It is a distribution shaped by history. Natural processes fractionate isotopes in patterned ways, and those patterns are not arbitrary. Lighter isotopes react faster, diffuse faster, and evaporate more readily, which shifts ratios during melting, evaporation, and precipitation. In carbonates, oxygen isotopes track temperature and water sources, while in sulfides, sulfur isotopes track redox conditions. The key is that the bias is systematic. That predictable bias is a feature, not a nuisance, because it gives investigators a vocabulary. It lets them distinguish ordinary geochemistry from extraordinary sources, even when the rock has been altered. A river can sort isotopes one way, a hydrothermal system another way, and a nuclear reaction in a third. The patterns become comparable, like accents in a spoken language. The key is pattern recognition across multiple isotopes, not a single surprising number. One odd value can be contamination, instrument drift, or a local quirk of mineral chemistry, but a coherent suite becomes a story, especially when it matches the physics of known processes. In forensic work, redundancy is not luxury. It is survival. Oklo is our anchor because its story is confirmed, tested, and retested for decades. It shows how a nuclear process writes a distinct isotopic ledger, even when the reactor is gone. The discovery itself was almost accidental, emerging from routine checks of uranium ore. In 1972, analysts noticed that the U-235 content was slightly lower than expected, and that small deficit opened a door. The first entry in Oklo's ledger is depleted U-235, and it matters for a specific reason. 2 billion years ago, natural uranium had more U-235 than today, because U-235 decays faster than U-238. Today, natural uranium is about 0.72% U-235, but back then it was closer to the enrichment used in some modern reactors. That time-dependent ratio is a crucial constraint. Criticality also requires a moderator, and Oklo had one in the most ordinary form: water. Groundwater percolated through porous sandstone, slowing neutrons so they could sustain fission in U-235. Geometry mattered too, because the uranium had to be concentrated into zones thick enough to keep neutrons from escaping. In other words, the deposit had to be just right. When fission runs, U-223T5 is consumed faster than U-238, and the ore ends up with a deficit that resembles spent reactor fuel. The depletion is not uniform because reactor zones operate unevenly and then shut down. Some models even suggest cycling, where heat boiled water away, the reaction paused, and then resumed when water returned. The rock becomes a record of intermittent power, but depletion alone is not enough, and Oklo forces us to admit that. Geochemistry can move uranium around, and mining can mix ores from different sources, creating misleading averages. Uranium can be leached under oxidizing conditions and redeposited where conditions turn reducing. A simple deficit could be a transport story rather than a nuclear one. Oklo's case strengthens because the fission products match reactor physics, and that is a higher bar. The daughters appear in proportions that ordinary decay cannot generate, because fission yields have their own characteristic distribution. Fission splits heavy nuclei into mid-mass elements, and those elements appear as isotopic mosaics. The pattern is not just unusual, it is structured. Neodymium isotopes are a central clue, because neodymium sits in a part of the periodic table rich in fission products. Fission yields create distinctive Nd143, Nd145, and Nd146 patterns that align with sustained operation. These are not the ratios you get from slow, radioactive decay of uranium alone. They are the ratios you expect when nuclei are repeatedly split. Ruthenium isotopes add another independent check, and they are especially useful because ruthenium has multiple stable isotopes with different fission yields. Their ratios reflect fission yield curves and neutron capture histories inside a working reactor zone. Neutron capture can shift certain isotopes, leaving a subtle shadow of the neutron environment. When the numbers line up, coincidence becomes unlikely. Xenon isotopes trapped in minerals provide a gas phase record, and that record is unusually resilient. Noble gases resist chemical alteration because they do not readily form compounds. If xenon is trapped in a crystal defect or a fluid inclusion, its isotopic mix can preserve nuclear events long after the surrounding chemistry has changed. It is like finding smoke in a sealed jar. Together, these lines converge on one conclusion, and convergence is the point. A chain reaction occurred repeatedly, long enough to imprint multiple isotope systems. Each system has its own vulnerabilities, yet they agree in the same direction. That agreement is what transforms an intriguing anomaly into a solved case. Oklo also teaches containment, and this lesson is as important as the fission itself. Many fission products stayed localized, held in mineral lattices and controlled by redox chemistry. Some elements were immobilized by clays, others by phosphates, and some were trapped in uranium minerals that resisted dissolution. Over geologic time, the reactor zones behaved like natural waste forms. That matters for our larger question, because it hints at what could survive. If a past technology left nuclear waste, its survival would depend on the same mineral custody and the same hydrologic luck. Would waste remain concentrated, or would it be smeared into background by groundwater? Oklo suggests that at least some signatures can persist. Yet Oklo also warns us about false intuition, and the warning is easy to ignore. Something can look engineered because the physics is universal, not because intelligence intervened. A reactor is not automatically a reactor built by hands. Nature can assemble the prerequisites, and it can do so without leaving any artifact we would recognize. So how do investigators separate natural fractionation from industrial processing, especially when both can produce sharp contrasts? They ask whether the full isotopic pattern fits known pathways, and they demand that the pathway be physically plausible. A good hypothesis must explain not just one ratio, but the whole suite. It must also fit the geology that hosts it. Natural decay chains have signatures that are internally consistent, and they come with built-in relationships. Uranium and thorium series produce predictable daughter ratios and secular equilibria, which are states where production and decay balance. If a system has been closed long enough, certain ratios settle into expected values. If it has been open, the departures follow recognizable rules. Industrial enrichment leaves different fingerprints, and the differences are almost philosophical. It changes U-235 and U-238 without producing the fission product suite that reactors generate. Enrichment is separation, not transformation, so it shifts uranium isotopes while leaving neodymium and ruthenium largely untouched. That mismatch can be diagnostic. Enrichment also tends to separate isotopes cleanly, and clean separation has a particular look. It can create sharp shifts in uranium ratios without corresponding shifts in rare earth fission products. In a natural system, processes are messier, often dragging multiple elements along together. A too neat uranium anomaly invites scrutiny. Reprocessing and reactor burnup create yet another pattern, and it is more complex than enrichment alone. They produce correlated anomalies across uranium, plutonium, neodymium, xenon, and other products. Burnup changes fission yields over time, and neutron capture creates secondary isotopes that depend on reactor conditions. The result is a multidimensional fingerprint. The forensic approach is comparative, and it is deliberately skeptical. You test competing hypotheses against the same dataset, then ask which requires the fewest special assumptions. If one explanation needs a chain of unlikely events, it becomes weaker. The strongest story is the one that fits both the chemistry and the geology with minimal strain. This is why looks processed is not a conclusion, and it never should be. It is an invitation to model geochemical transport, mineral partitioning, and mixing histories. Investigators ask how fluids moved, when minerals formed, and which phases could host which elements. They also ask what later events might have overprinted the original signal. Groundwater can mimic intention by sorting elements, and it can do so with startling sharpness. Redox fronts can concentrate uranium and rare earths, creating boundaries that resemble design. Under oxidizing water, uranium becomes soluble and mobile, but under reducing conditions it precipitates abruptly. A natural chemical gradient can draw a line as crisp as a blueprint. Metamorphism can reset some isotope systems, and that complicates any deep-time claim. Heat and fluids can blur original ratios, making a natural anomaly appear more exotic, or making an exotic anomaly look ordinary. Some minerals close to diffusion at high temperatures, while others remain robust. The rock's thermal history becomes part of the evidence, so investigators look for redundancy, and they look for minerals that behave like vaults. If multiple isotope systems agree, the signal is more likely to be real and primary. If one system is disturbed but another is intact, the contrast can even reveal the timing of alteration. In that sense, overprinting can become information. They also look for context in the rock record because chemistry alone is not enough. A reactor signature should sit in a plausible host geology with moderators, geometry, and time-appropriate uranium ratios. It should also fit the sedimentary environment that could concentrate uranium in the first place. The isotopes must be consistent with the setting. Oklo passes those tests, and that is why it remains the benchmark. It is local, constrained, and consistent with known physics and geochemistry. The reactor zones occur in a specific stratigraphic interval, and the anomalies are not randomly scattered. The story has boundaries, which is what real stories in geology tend to have. Now we widen the search without overstating claims. The goal is not to declare lost civilizations because declarations are cheap and tests are hard. The goal is to map anomaly classes worth testing, then ask what the most conservative explanations can and cannot cover. In other words, we build a catalogue of interesting, not yet extraordinary. One class is platinum group element spikes, which stand out because these elements are usually scarce in crustal rocks. Iridium, platinum, and osmium can rise sharply in layers, hinting at unusual inputs. In a stratigraphic column, the spike can look like a thin dark seam, an instant in time compressed into millimeters. The question is what delivered it. The most famous natural explanation is impact debris, and the logic is straightforward. Meteorites are enriched in PGEs, and impacts can spread a thin global layer as dust settles through the atmosphere. Some impacts also create shocked minerals, microtectites, and high-pressure phases that act as supporting evidence. When those markers co-occur, the case strengthens. Volcanism can also elevate PGEs, and it does so through different pathways. Large igneous provinces can mobilize metals and distribute them through aerosols and ocean chemistry. Basaltic magmas can carry sulfur-rich melts that scavenge platinum group elements, then release them during eruption. The signal can be regional or global depending on scale, so the forensic question becomes distribution, because distribution encodes mechanism. Impacts tend to produce brief, globally synchronous spikes with shocked minerals and ejector markers. Volcanism tends to produce longer intervals linked to ash layers, mercury anomalies, and climate proxies that track sustained outgassing. Timing and texture become as important as chemistry. A technological explanation would need a different pattern, and it would need to earn its place. It would need element ratios and co-occurring industrial markers that natural sources do not predict. It would also need a plausible pathway for global dispersal or localized concentration. Without that, unusual remains only unusual. Another class is carbon isotope excursions, and carbon is central because it connects air, ocean, rock, and life. Carbon-12 and carbon-13 ratios shift when the carbon cycle is disturbed. These shifts are recorded in carbonates, organic-rich shales, and even some fossil materials. In the lab, the numbers become a curve, and the curve becomes a narrative. Biology fractionates carbon strongly, and that fractionation is one reason carbon isotopes are so informative. High productivity and organic burial can drive carbon-13 enrichment in carbonates and depletion in organic matter. When more light carbon is locked away in sediments, the remaining dissolved carbon becomes heavier. The ocean, in effect, keeps score. Methane release can drive the opposite direction, and it can do so rapidly. Methane is carbon-12 rich, so rapid release can produce sharp negative excursions. If methane hydrates destabilize, or if wetlands expand under warming, the atmosphere can shift quickly. In sediments, that shift can appear as a sudden plunge. Ocean circulation changes can also move the signal, and this is where interpretation becomes delicate. Anoxia, stratification, and carbonate dissolution can alter what sediments record, even if the global carbon inventory changes only modestly. Local basins can amplify or mute the global story. That is why investigators compare many sites rather than trusting one. Industrial carbon burning would have its own expectations, and the expectations are testable. It would inject old carbon-12 rich carbon quickly, and it could pair with metal pollution signals. It might also be accompanied by nitrogen isotope changes if agriculture or combustion altered the nitrogen cycle. The challenge is that deep time erases many of the obvious companions, but deep time complicates detection, and it complicates it in predictable ways. The carbon cycle mixes, buffers, and re-equilibrates, so the isotopic spike may be smeared. Bioturbation can blur layers, diagenesis can alter carbonates, and later metamorphism can reset the record. The signal can survive, but it rarely survives untouched. A third class is sulfur isotope mass-independent fractionation, a phrase that sounds technical because it is. In the early atmosphere, ultraviolet photochemistry created sulfur signatures that break normal mass rules. Instead of fractionation scaling smoothly with mass differences, the isotopes shift in ways that reflect photochemical pathways. It is chemistry behaving like a fingerprint of sunlight. These signals appear in Archean rocks and fade after oxygen rose, and that timing is part of their power. They are not evidence of technology, but they are a template for atmospheric forensics. They show that a planet's air can leave a durable isotopic imprint in minerals like pyrite and barite. They also show that global transitions can be tracked across continents. That template matters for technosignatures because it expands our imagination responsibly. A civilization might leave a global atmospheric change that is easier to detect than local artifacts. Would such a change be abrupt or gradual, and would it be chemically distinctive? The sulfur record reminds us that air chemistry can be archived, even when everything else is gone. This brings us to radionuclides that seem out of place, a category that tempts speculation. Not every radioactive isotope is suspicious, even when it is rare. Earth has multiple natural factories for radionuclides, and they operate continuously. The trick is to know which factory is responsible. Cosmogenic isotopes are expected, and they are produced by cosmic rays striking the atmosphere and surface. These interactions produce nuclides like beryllium-10 and carbon-14, and their presence tracks exposure and climate. In ice cores, they can record solar variability, while in sediments they can record erosion and deposition. They are exotic, but they are not alien. Natural decay chains are expected too, and they are ubiquitous in crustal rocks. Uranium, thorium, and potassium produce predictable daughter products across many environments. Radon gas can migrate and deposit its daughters on surfaces, creating local anomalies that look dramatic. Even here, context and pattern decide meaning. What would be truly suspicious are long-lived artificial isotopes, because longevity is the price of persistence. Some transuranics and certain fission products could persist for millions of years. If they were present in unusual abundances, they might stand out against natural backgrounds. But even then, the burden of proof would be heavy. Yet suspicion requires caution, because nuclear chemistry has natural loopholes. Many candidate isotopes have half-lives too short to survive deep time, and others can be produced by rare natural reactions. Neutron capture in unusual environments can create isotopes that look manufactured at first glance. Nature is not limited to one pathway. Oklo itself produced plutonium-239 briefly through neutron capture, and that detail matters for our reasoning. That plutonium decayed, but it demonstrates that nature can generate transuranic pathways under the right neutron flux. If we found traces of a transuranic daughter, we would have to ask whether a natural reactor could have made it. Oklo expands the list of plausible natural sources, so the test becomes specificity and persistence, not mere rarity. Do we see an isotope that is hard to make naturally, in a pattern hard to transport naturally? Does it occur with the expected companions? And does it sit in a stratigraphic context that makes sense? A single number is never enough. Investigators also ask about co-occurrence, because technology is rarely chemically isolated. A true technological radionuclide signal would likely accompany enrichment patterns, fission-xenon, or unusual metal distributions. It might also show spatial structure, such as gradients away from a source. Co-occurrence turns a curiosity into a hypothesis with teeth. This is where global versus local signals matters, and it matters because scale changes what survives. A civilization could alter the atmosphere, oceans, and sediments at planetary scale, leaving a signature that is diffuse but widespread. Alternatively, it could leave intensely local scars that are easy to miss unless you drill the right place. Both possibilities demand different search strategies. Global signals should appear in many basins of the same age, and they should be correlatable. They should correlate across continents, not just in one mine or one core. They should also align in time within dating uncertainties, because a global event has a global clock. When correlation fails, local explanations regain strength. Local signals can still be decisive, and Oklo is the proof. Oklo is local, yet its isotopic suite is so diagnostic that the conclusion is secure. It does not need global confirmation because the physics is written directly into the rock. Sometimes a single site can be enough, if the signature is specific enough. For a lost technological society, local signals might include waste repositories, mining districts, or industrial sediments, but they would be patchy and easy to miss. They might be buried under younger deposits, subducted, or metamorphosed beyond recognition. Even if they survived, they might resemble ordinary ore bodies at first glance. How many anomalies have been logged and then forgotten because they seemed too small? Global signals might include abrupt greenhouse shifts, widespread metal pollution, or novel isotope ratios in carbon and nitrogen, but they would still need natural explanations ruled out. Earth has produced dramatic climate swings without industry, and it has spread metals through volcanism and erosion. The standard of evidence must remain high, because the claim is extraordinary. The point is not to believe, but to discriminate. The discipline is to treat every anomaly as a hypothesis test, and to do it in the right order. First ask what known Earth processes can do, then ask what remains unexplained, then ask what additional measurements could reduce ambiguity, rather than merely adding intrigue. A good investigation is designed to be disappointed by easy answers. This is also where the great filter frame returns, not as a conclusion, but as a pressure. If intelligence is fragile, its traces might be brief, localized, and quickly overwritten by erosion and tectonics. Even a global industrial era could be a thin layer, vulnerable to mixing and chemical recycling. The silence of the rocks might be telling us about survival, not just about existence. Oklo gives us calibration for that fragility, and calibration is what science needs most. It shows how a high-energy process can leave a durable isotopic scar without leaving a visible monument. There are no towers, no pipes, no slag heaps, only ratios and minerals. The rock remembers the reaction, even when it forgets the machinery. It also shows the opposite danger, and this danger is psychological as much as scientific. A dramatic-looking signature can be purely natural, and our pattern-hungry minds can overread it. We want stories, and geology offers stories generously, but not always the ones we expect. The antidote is method, so the forensic toolkit must be conservative, and it must be explicit about uncertainty. It must prefer multiple independent isotopic lines, clear stratigraphic context, and reproducible measurements. It must also document contamination controls, standards, and analytical precision, because small biases can mimic big claims. In the end, the numbers must survive skepticism. From here, the story shifts again, because chemistry is only one archive. Chemistry can whisper across billions of years, but life leaves louder echoes when it changes suddenly. When ecosystems collapse, the record can become stark, with disappearances and replacements written into fossil assemblages. If something ended earlier worlds, we might see it in extinctions. The next chapter follows the biological record where the planet's edits become abrupt, and where the silence of missing species can be louder than any isotope ratio. We will ask what kinds of shocks can rewrite life's diversity, and how quickly those shocks can propagate. In that record, the clues are not just atoms, they are absences. Chemistry can whisper across billions of years, but life leaves louder echoes when it changes suddenly. In the rocks, slow processes read like paragraphs, yet abrupt collapses look like underlined sentences, thin, sharp, and impossible to ignore. The fossil record is not only a catalogue of forms preserved in stone, it is also a record of interruptions, where diversity drops fast and recovery takes longer. When paleontologists talk about extinction, they're really talking about two different clocks. One clock measures the steady churn of evolution, where new species appear as others fade. The other clock measures crisis, when the normal rules of replacement break down. A mass extinction is defined by magnitude and by rate, because losing many species slowly is not the same as losing them in a geologic instant. Background extinction is the normal loss of species as environments shift and lineages compete. It is the quiet attrition of ecosystems, happening as climates drift, continents move, and predators and prey co-evolve. Mass extinction is a spike above that baseline, where many groups disappear across many habitats. It is not merely a bad century for biodiversity, but a systemic failure across the biosphere. Rate matters because it separates slow replacement from shock. If losses unfold over millions of years, populations can migrate, adapt, and reorganize. If losses unfold over thousands of years, the options narrow quickly, and even resilient systems can snap. In deep time, even 10,000 years can look like a knife cut. The question is not only what died, but how quickly the killing spread. That speed is difficult to grasp because our instincts are tuned to human lifetimes. In the field, a boundary can be a seam of clay you can cover with a palm. Above it, one community of fossils, below it, another. The rocks remind us that catastrophe can be both enormous in effect and tiny in thickness. Earth's history includes the Big Five mass extinctions, plus other rapid crises that nearly qualify. End Ordovician links to glaciation and sea level fall, when ice locked up water and shallow seas drained away. Late Devonian is prolonged and complex, with repeated pulses and reef collapse that hint at long-term instability. Each event is a different experiment in how life fails. End Permian is the largest, with extreme losses in oceans and on land. End Triassic clears ecosystems before dinosaurs dominate, opening space for new architectures of life. End Cretaceous ends non-avian dinosaurs and reshapes marine food webs, leaving survivors to rebuild under new skies. These are the famous markers, but they are also warnings written in different handwriting. They are not single stories with one cause, and that is the first tension. Many extinctions show multiple stresses that overlap in time, sometimes stacking like waves. A planet can be pushed by volcanism, then tipped by impact, then locked into feedbacks. The hardest part is not naming a culprit, but tracing the sequence of pressure points. To measure speed and cause, we rely on proxy records. Proxies are indirect measurements preserved in rock, ice, and fossils, because the ancient world did not leave thermometers and gas analyzers. They convert chemistry and texture into timelines of temperature, oxygen, and carbon cycling. In practice, that means reading tiny shifts in isotopes, minerals, and sediments, as if they were instrument panels. Some proxies are event markers that behave like timestamps. Iridium layers point to extraterrestrial dust because iridium is rare in crust but common in meteorites. Shocked quartz and high-pressure minerals point to impacts because they require extreme pressures, far beyond ordinary tectonics. When those signals align across continents, the case becomes difficult to dismiss. Other proxies track sustained processes rather than single instants. Mercury spikes can indicate large-scale volcanism because mercury is emitted in volcanic gases and can travel widely before settling. Sediment laminations can indicate anoxia because undisturbed layers imply low oxygen and low burrowing. In healthy seafloors, worms and other organisms churn sediment like ploughs, erasing delicate layering. Isotopes are the backbone because they scale from local to global. Carbon isotopes record carbon injection and burial as excursions in carbon-13, which shifts when the system receives carbon from different reservoirs. Oxygen isotopes in carbonates record temperature and ice volume through fractionation patterns, because heavy and light oxygen partition differently as water evaporates and minerals precipitate. These ratios are subtle, yet they can map planetary change. Even the fossils themselves can function like proxies, because organisms are sensitive instruments. Reef builders vanish when water chemistry turns hostile, and plankton communities rearrange when temperatures and nutrients shift. A change in shell thickness, body size, or geographic range can be a biological readout of stress. The biosphere records climate in its own anatomy. The record is imperfect, and we have to say that clearly. Sediments can be mixed by burrowing organisms and by currents, smearing what was once a sharp line. Diagenesis can alter original chemistry, and dating uncertainties can blur a sharp event. Sometimes the rock is less like a photograph and more like a painting that has been retouched. We also face the problem of uneven preservation, because not every environment leaves a clean archive. Deep-sea sediments may be continuous, but they can dissolve under acidic conditions. Shallow shelves preserve abundant fossils, yet storms and sea level shifts can erode sections. The best reconstructions come from stitching together many incomplete stories. Still, some case studies are unusually strong, and they anchor the chapter. They show how fast Earth can change without any technology, simply through physics and chemistry. They also show where the speculative question could even fit, because the timing is tight enough to tempt suspicion. If a collapse can happen quickly, it invites us to ask what quickly really means. Begin with the end Permian, the closest thing to a planetary near-death experience. Around 252 million years ago, ecosystems collapse across oceans and continents, leaving a world that looks emptied out. Many marine species vanish, and forests thin or disappear in some regions. In some places, the landscape shifts toward hardy survivors, spore plants and opportunists that tolerate stress. The leading driver is the Siberian Traps, a flood basalt province of immense scale. Imagine lava not as a single volcano, but as repeated outpourings that blanket vast areas, building layer upon layer. Basalt eruptions release carbon dioxide, sulfur gases and heat, and the emissions do not stop after one season. Intrusions into carbon-rich sediments can add methane and other volatiles, effectively turning buried carbon into atmospheric forcing. Flood basalts matter because they combine duration with magnitude. A single eruption can darken skies and acidify rain, but repeated pulses can push the climate into a new regime. The Siberian Traps likely erupted in episodes, separated by quieter intervals that still carried degassing. Each pulse is a shove, and the system may not fully recover between shoves. Warming follows, and the warming is not gentle. Higher temperatures reduce oxygen solubility in seawater, which means warm oceans hold less breathable gas. Stratification can increase, and circulation can weaken, starving deep waters of oxygen. Once deep waters stagnate, the ocean's internal ventilation system begins to fail. Ocean anoxia becomes a central mechanism because it kills from below. In anoxic waters, decay consumes remaining oxygen and can produce hydrogen sulfide, a toxic gas that can poison animals directly. That chemistry stresses animals and disrupts food webs because the base of the system, microbes and plankton, changes first. When the bottom of the pyramid shifts, everything above it wobbles. Anoxia also changes nutrient cycling in ways that can lock in crisis. Phosphorus can be released from sediments under low oxygen, fertilizing surface waters and driving more productivity. More productivity means more sinking organic matter, which means more decay and oxygen consumption at depth. The ocean can enter a feedback loop where low oxygen breeds even lower oxygen. We see anoxia in black shales and in laminated sediments that lack burrow traces. We see redox shifts in trace metals that change solubility with oxygen levels, such as uranium, molybdenum and vanadium. We see carbon isotope excursions that imply major carbon cycle disruption, as if the planet's accounting system for carbon suddenly went out of balance. These are not one-off clues, but a converging pattern. Mercury anomalies appear near some extinction intervals, consistent with large volcanic emissions. Mercury can attach to particles and settle into sediments, leaving a chemical shadow of atmospheric loading. The match is not perfect everywhere, and that matters. It suggests complex timing, multiple pulses, and regional differences in deposition. The end Permian also raises the speed question in a sharp way. Some kill phases may occur in tens of thousands of years, perhaps less, depending on how layers are dated and correlated. In geology, that is abrupt, and it invites the idea of compounding triggers. When multiple mechanisms operate on similar timescales, the result can look like a sudden switch. Compounding does not require intelligence, and we should not imply it does. Flood basalts can pulse, and each pulse can push climate further toward thresholds. Feedbacks can amplify, including methane release, wildfire, and reduced carbon burial. A stressed biosphere can also become more flammable, turning forests into fuel and adding soot and CO2 to the air. Visualize the Permian world as a sequence of tightening constraints. The oceans warm and stratify, then oxygen retreats into thin surface layers. Coastal seas become hostile, then the open ocean follows. On land, heat waves intensify, and rainfall patterns shift, and plant communities fragment. It is not a single blow, but a tightening net. Now shift to the end Cretaceous, the best-known catastrophe because its markers are clean. Around 66 million years ago, a global boundary layer appears in many sections, like a line drawn across the planet's diary. It contains iridium enrichment and impact ejecta, often mixed into a clay that stands out from surrounding sediments. That boundary is a rare gift to geologists because it synchronizes distant sites. Chicxulub is the crater buried under the Yucatan, and its size matches the scale of global disruption. Shocked quartz, microtectites, and spherules fit an impact origin because they form when rock melts and recondenses in flight. The distribution and grain types support a global atmospheric dispersal. Even without seeing the crater, the debris tells the story. The impact delivers immediate effects that scale globally. Dust and aerosols reduce sunlight, collapsing photosynthesis, and that collapse ripples upward through food webs. In the ocean, plankton productivity drops, and the effects reach fish, reptiles, and filter feeders. On land, plant growth falters, and herbivores lose their base, dragging predators down with them. Wildfires may spread in some regions, though soot evidence varies by site and interpretation. Some deposits suggest intense heating and widespread burning, while others imply patchier fire regimes. That ambiguity is important, because it reminds us that even global events have regional expressions. A catastrophe does not land evenly on every ecosystem. There is also the matter of timing, because instant in geology still has structure. The impact's first hours and days are about heat, shock, and ejecta. The following months and years are about darkness, cold snaps, and disrupted rainfall. Then the longer recovery begins, with altered oceans and reshaped habitats. But the end Cretaceous is not impact alone in many models. Deccan Trap's volcanism overlaps in time, adding greenhouse gases and aerosols over longer intervals. Lava flows in India build thick stacks, and volcanic gases can perturb climate repeatedly. The combined stress may explain patterns that a single trigger struggles to fit, especially when extinctions appear staggered in some groups. Here, the proxy logic becomes a lesson in discrimination. Iridium and shocked minerals point to a brief event because they arrive in a narrow layer. Mercury spikes and long warming trends point to sustained volcanism and climate forcing. The challenge is to separate what is synchronous from what is merely nearby in time. The boundary also shows how thin a global catastrophe can be in rock. A world-changing event can compress into centimeters of clay, sometimes capped by a layer of tsunami deposits near coasts. That thinness is why deep time can hide even dramatic episodes. If the sedimentation rate is low, an entire crisis can vanish into a line. In visual terms, imagine a cliff face with bands of limestone and marl, then a sudden dark seam. The camera lingers on that seam, and the narrator reminds us that it represents a planet-wide interruption. Above the seam, different shells dominate, and familiar forms are gone. The rock is quiet, but the implication is loud. Next, move to a rapid climate event without a classic mass extinction. The Paleocene, Eocene thermal maximum, about 56 million years ago, is a sharp warming pulse that leaves a clear geochemical signature. Temperatures rise quickly and oceans acidify, stressing organisms that build carbonate shells. It is a crisis of chemistry more than a single physical blow. The PETM is defined by a strong negative carbon isotope excursion. It implies rapid injection of carbon-12 rich material into the ocean atmosphere system, because biological carbon tends to be lighter in isotopic terms. Candidates include methane hydrates, volcanic intrusions, and oxidation of organic carbon. Whatever the source, the system received a large dose of light carbon in a short time. We track warming through oxygen isotopes and through changes in microfossil assemblages. We track acidification through carbonate dissolution horizons in deep-sea sediments, where shells dissolve and leave a ghostly gap. We track ecosystem response through migrations, dwarfing, and turnover. The biosphere responds not only by dying, but by moving and shrinking under stress. The PETM shows that a planet can shift climate on 1,000-year timescales. In some records, the onset appears especially abrupt, though the exact pace depends on dating and sedimentation. Recovery takes far longer, as carbon is reburied and weathering draws down CO2. The imbalance lasts long enough to reshape ecosystems without wiping them out. This matters because it separates collapse from extinction. A system can be pushed into a new state and remain biologically rich, yet fundamentally reorganized. The PETM is a reminder that disruption has degrees, and not all filters are guillotines. Some are long corridors of stress that favor certain strategies over others. These three cases frame a key point about filters. A great filter does not need to be a single apocalyptic moment that ends everything at once. It can be a bottleneck that repeatedly trims complexity until only simpler strategies persist. The rocks may record a series of narrowing passages rather than one locked door. A bottleneck is a reduction in population size and diversity that limits what can survive. It can be global, like ocean anoxia, or regional, like prolonged drought that fractures habitats. It can also be selective, sparing some lineages while erasing others. In every case, what survives is not always what seems best, but what happens to fit the moment. Speed changes the odds because adaptation needs time. If climate shifts faster than migration and evolution can track, extinction rises, even among once dominant groups. If multiple stresses overlap, resilience breaks even in robust ecosystems. The uncomfortable implication is that stability is a resource, and it can be spent quickly. This is where the speculative angle enters, and it must be framed carefully. We ask a constrained question, not a sensational one, because the rocks deserve discipline. Could any collapse be technologically amplified, and how would we tell? The point is not to force an answer, but to define what evidence would even look like. Technological amplification could mean deliberate or accidental forcing that stacks onto natural stress. It could mean greenhouse gas release that accelerates warming already underway, pushing a system past thresholds sooner. It could mean nutrient loading that worsens anoxia in vulnerable seas, turning coastal dead zones into broader oxygen crises. These are familiar mechanisms, but the question is scale and signature. To be useful, speculation has to be falsifiable, which is a scientific way of saying it must risk being wrong. A technological catastrophe should leave chemical patterns that are hard for nature to mimic. It should also appear in stratigraphy with a timing that matches rapid change. If the signal is vague, it will always be swallowed by natural explanations. Start with nitrogen, because agriculture and industry can reshape the nitrogen cycle. Fertilizer scale fixation can alter nitrogen isotope ratios in sediments, especially when excess nutrients drive eutrophication. A global shift in delta 15N could appear alongside indicators of algal blooms and low oxygen. In modern systems, such shifts can be dramatic and fast, yet nitrogen is also mobile and biologically processed, which complicates interpretation. Denitrification and nitrogen fixation occur naturally and can shift isotopes, sometimes in opposite directions depending on oxygen and nutrient conditions. We would need a pattern that is abrupt, widespread, and coupled to other anomalies. Without that coupling, nitrogen alone is too ambiguous. Consider synthetic organics and halogenated compounds, because they are distinctive in modern pollution. Persistent molecules could leave unusual biomarkers or breakdown products, especially if they bind to sediments and avoid oxidation. Some might survive burial under the right conditions, protected in anoxic muds. The idea is not that a plastic bag fossilizes intact, but that chemistry leaves residues. But deep time is hostile to many complex molecules. Heat, pressure, and microbes tend to reduce organics towards simpler hydrocarbons, erasing the fine structure that would scream manufactured. A convincing signal would likely be indirect, like unusual halogen distributions or resistant residues. Even then, the signal would have to be global enough to stand above local quirks. Consider metals and industrial particulates, because mining and combustion move elements fast. A technological interval might show sharp spikes in lead, copper, chromium, or platinum group patterns, especially if aerosols distribute them widely. It might also show soot and fly ash type particles with distinctive textures. In modern sediments, combustion spheres can be diagnostic under a microscope. Nature can also spike metals through volcanism and hydrothermal activity. Mercury spikes already show how a natural source can mimic industrial dispersal, and ash can carry many elements together. The key would be a multi-element fingerprint that matches industrial ratios, not volcanic ones. That fingerprint would need consistency across basins, not just a single anomalous site. Consider radionuclides, because nuclear technology has unique products. Distinctive fission xenon patterns, unusual neodymium suites, or long-lived artificial isotopes would be strong, because they are hard to generate accidentally at scale. But many candidate isotopes decay too fast to survive deep time. The deeper we look, the more the clock erases the most obvious signatures. Oclo is the caution sign here, because nature can run nuclear processes locally. In Gabon, natural uranium deposits achieved criticality in the past, leaving isotopic anomalies without any technology. A nuclear-like signal would need context that rules out natural reactors. It would need patterns inconsistent with known uranium ore geometries and groundwater moderation. All of this runs into the same geological reality. Earth is a recycler. Sediments are subducted, rocks are metamorphosed, and oceans dissolve and redeposit minerals. Even when layers survive, they can be altered, mixed, or eroded. The planet does not preserve every message, and it rarely preserves it in pristine form. In practice, we largely do not see these technological signatures in deep time. That absence does not prove they never existed, because absence can be a preservation problem. It does set constraints on how common, how global, and how long-lived such civilizations could have been. If they existed, they likely left either subtle traces or traces that were later destroyed. It also highlights how often natural explanations already fit the data. Impacts leave iridium and shock, and they leave craters when the crust cooperates. Flood basalts leave mercury and long warming, and they leave thick volcanic provinces. Anoxia leaves laminations and redox-sensitive metals, and it leaves biological turnovers consistent with oxygen stress. Nature is fully capable of producing dramatic planet-wide signatures, so the honest stance is a narrow window for the speculative claim. A technological collapse might be detectable if it was global, chemically distinct, and preserved in multiple basins. If it was local or brief, the shredder likely erased it. The rocks do not invite certainty, but they do allow constraints. This returns us to the great filter logic inside Earth history. Filters can be external, like impacts, or internal, like runaway climate feedbacks that the planet triggers on its own. For a technological species, the most dangerous filters may be self-triggered, then masked by geology. The unsettling thought is not that the past was artificial, but that the past shows how easy collapse can be. Now introduce the ecological reset concept, because extinction is not only an ending. After collapses, niches reopen and survivors diversify, often in bursts that look like evolutionary improvisation. Food webs rebuild, and evolutionary experiments restart with new constraints. In the wake of loss, opportunity returns, but it returns unevenly. Reset does not mean the planet returns to the same state. It means the competitive landscape changes, and new body plans can dominate where old ones once ruled. The early Triassic seas, for example, were not simply Permian seas minus a few species. They were reassembled ecosystems with different winners and different vulnerabilities. Resets also carry a biological memory of stress. After a crisis, ecosystems can be simplified, with fewer large predators and fewer complex interactions. That simplification can persist for millions of years, even after diversity begins to rise. Recovery is not just about numbers, but about rebuilding intricate relationships. Intelligence, if it is not a fluke, could arise again given enough time. Yet intelligence is expensive, requiring stable energy flows and long developmental windows, and those are fragile in chaotic climates. Complex brains demand reliable food webs, predictable seasons, and long lifespans. If bottlenecks recur too often, intelligence may be filtered out before it scales. This is where the central question sharpens without being answered. If earlier technological species existed, they faced the same scythe we see in the strata, and their traces would have to survive the same recycling. If they did not exist, these extinctions still warn that intelligence is not protected. Either way, the rocks teach humility. The chapter's tension is not that extinctions look artificial. The tension is that some collapses are fast enough to feel like switches, especially when seen as thin layers in stone. In that narrow gap, compounding triggers can hide the difference between accident and amplification. The boundary between natural and unnatural is not philosophical, but evidentiary. So we end by widening the lens from life to the planet's atmosphere. Extinctions are Earth's scythe, cutting down complexity when conditions swing, and the blade is sharpened by feedbacks. But before complex life even dominated, Earth underwent a transformation that might be the biggest filter of all. It was not a crater or a lava field, but a change in the air. Oxygen changes chemistry, energy, and what can survive in rock. It rewrites oceans, minerals, and metabolisms, and it can be both poison and power, depending on who is breathing. The next chapter follows that transformation, where the filter is not impact or lava, but air itself. "2 billion years ago, Oklo ran in silence, and the rocks kept the accounting. In the dark pores of sandstone, water moved like a slow blood stream, moderating neutrons, closing the circuit and then drifting on. There were no warning lights, no containment domes, only heat threading through mineral grains and disappearing into groundwater. That reactor sits near a deeper turning point, because Earth itself was changing into something chemically alien to us. The same planet that could assemble a critical mass was also learning, through life, how to oxidize its own skin. Before oxygen, the atmosphere held only traces of free O2, and those traces rarely lasted. The air was instead thick with reactive gases, shaped by volcanism, lightning, and ultraviolet light. Carbon dioxide, nitrogen, water vapor, and reduced gases like methane and hydrogen sulfide could dominate, depending on region and time. Without an ozone layer, ultraviolet photons reached lower altitudes and drove reactions that modern skies simply do not allow. Even the color of the sky may have been different: hazy, chemically active, and tinted by aerosols born from sunlight and volcanic breath. The oceans were largely anoxic, often iron-rich, and tinted by dissolved metals that would be impossible in today's seas. In that water, ferrous iron could remain dissolved for long stretches, because nothing forced it into rust. Some basins may have been greenish or brown, not from algae, but from chemistry and suspended minerals. Hydrothermal vents injected reduced compounds, and currents carried them into gradients where energy waited to be harvested. Microbial life dominated nearly every ecological niche, from sunlit shallows to hydrothermal gradients that never saw daylight. Life's main architects were bacteria and archaea, trading electrons in darkness and shallow light. Their world was built from redox chemistry, who could steal energy from sulfur, iron, hydrogen, or carbon compounds without wasting it. In that world, complexity meant chemistry, not bodies, and survival meant tolerating scarcity across long, unstable intervals. Many metabolisms were essentially negotiations with the environment, tuned to whatever electron donors and acceptors happened to be nearby. Even the shoreline would have looked unfamiliar, because soils were thin, plants did not exist, and rock weathered under a different sky. Oxygen was not a gift at first, because oxygen is aggressively reactive. A molecule of O2 is stable enough to persist, yet eager enough to rip electrons from vulnerable bonds. For most early organisms, O2 attacked proteins, membranes, and DNA through oxidative stress, turning metabolism into a liability. Reactive oxygen species formed easily: peroxide, superoxide, hydroxyl radicals, and cells without defenses were chemically burned from the inside. The danger was not abstract, because a single radical can start a chain reaction that tears through lipids like a spark in dry grass. What we call breathable air would have been a toxin cloud to much of early life. Even small increases in oxygen can overwhelm primitive biochemistry, because damage accumulates faster than repair. The problem is not only oxygen itself, but what oxygen becomes when it meets metal ions and sunlight. Iron and copper can catalyze reactions that generate radicals, so a cell's own nutrients can become weapons. It is a chemistry of chain reactions, where one spark can cascade through a cell's most essential machinery. This is the first reframing of the Great Filter in Earth terms. It is not one wall in space, but a sequence of planetary gates, each one a transition that can fail, stall, or reverse. Even after life succeeds, the planet can still veto the next chapter. Earth's history is not a straight line upward, but a staircase with missing steps. The unsettling implication is that a living world can remain microbial for eons, not from lack of life, but from lack of stable permission. The Great Oxidation event arrives as the most famous of these gates. Around 2.4 to 2.1 billion years ago, multiple lines of evidence show a step change in atmospheric chemistry. The record is not a single spike, but a shift that propagates through minerals, isotopes, and sediments across the globe. It is written in rocks the way a fever is written in a body, distributed, persistent, and unmistakable. If you could watch the planet in time-lapse, the change would look like a slow brightening of chemical possibilities. Start with iron, because iron is an oxygen meter written into the ocean. In an anoxic sea, dissolved ferrous iron stays mobile and abundant, slipping through water like an invisible dye. When oxygen appears, iron oxidizes into ferric forms, precipitates, and settles as layered deposits. Banded iron formations capture this transition, recording pulses when oxygen production outpaced the ocean's capacity to absorb it. Each pulse implies that oxygen was being made faster than the sea could hide it. Visually, those bands are like planetary tree rings, dark and light layers stacked with patient precision. Hematite and magnetite alternate with silica-rich layers, as if the ocean kept changing its mind. Each layer implies a chemical season, where oxidants surged and then were consumed. The iron did not simply vanish, it moved from dissolved ions to solid minerals, locking away a history of changing seawater. When you run a hand across a polished slab, you're touching the residue of an ancient redox battle. Then sulfur, because sulfur isotopes preserve the sky's photochemistry. In the Archean, mass-independent fractionation appears in sulfur minerals, a signature of ultraviolet reactions in an oxygen-poor atmosphere. It is a subtle fingerprint, created when sunlight splits sulfur-bearing gases without the buffering presence of an ozone shield. After oxygen rises, that EMF signal collapses because ozone and oxygen reroute the photochemical pathways. The atmosphere stops behaving like a raw laboratory and starts behaving like a regulated system. The disappearance is a global timestamp that something fundamental changed above the oceans. It is not merely that oxygen existed somewhere, sometimes, but that the atmosphere's overall chemistry crossed a threshold. Ozone begins to form more reliably, and ozone changes the rules of ultraviolet light. The sky itself becomes a filter, reshaping what radiation reaches the surface and what reactions can occur. A thinner UV field also changes mutation pressures, which quietly alters evolutionary pacing. Then red beds, because continents remember oxygen differently than seas. Oxidized iron minerals stain ancient sediments red when atmospheric oxygen becomes persistent. Red beds are not proof of a single day of oxygen, but they imply a new baseline that lasted through seasons and storms. They tell us the surface environment began living in an oxidizing regime, where exposed minerals could no longer remain chemically reduced. The land for the first time starts to keep oxygen's signature in broad daylight. Imagine the visual shift, cliffs and floodplains taking on rust tones, not because of life, but because of air. Rivers carry sediments that have already been oxidized upstream, and those sediments keep their color as they settle. Dust storms lift iron-stained grains into a sky that is slowly becoming less reducing. The land begins to archive oxygen in plain sight, while the sea continues to hide it in deeper chemistry. The planet's palette changes, and that change is a geochemical announcement. Cyanobacteria sit at the center of this story, because they learned a dangerous trick. Oxygenic photosynthesis split water, released O2, and stored energy in organic matter. It was a metabolic breakthrough that scaled, because sunlight is abundant and water is everywhere. The byproduct was a planetary pollutant, and the pollutant was oxygen. In microbial mats, that oxygen could build up locally, then leak into water and air like a slow, persistent exhaust. The trick is worth lingering on because splitting water is hard. It requires a catalytic machinery that can pull electrons from one of the most stable molecules available, then route that energy into building sugars. Photosystem 2, with its oxygen-evolving complex, uses manganese and calcium to manage a reaction that would otherwise be violently inefficient. In plain language, cyanobacteria learn to run on sunlight and water, and the exhaust was a reactive gas. Once that pathway existed, it could spread across shallow seas and microbial mats like a slow ignition. At first, oxygen did not accumulate because Earth had sinks hungry enough to eat it. Reduced iron, volcanic gases, and exposed minerals consumed O2 as fast as microbes produced it. In the oceans, oxygen met dissolved iron and disappeared into rust that sank into darkness. In the air, oxygen reacted with methane and other reduced gases, thinning the atmosphere's old chemical character. The planet was buffering the toxin, keeping it mostly local, mostly oceanic, mostly temporary. Oxygen oases could appear near productive microbial mats, then collapse when currents shifted or sinks caught up. You can imagine a shoreline lagoon where the water above a mat turns briefly oxygenated, while a few centimetres below remains lethal to oxygen. The journey begins when production and burial finally outrun those sinks, and when the bookkeeping stops balancing. That moment is not a single day, but a change in the planet's long-term budget. Burial matters because carbon locked away in sediments is oxygen not immediately reconsumed by decay. This is where the filter logic becomes sharp. A biosphere can transform a planet, but the transformation can kill the biosphere that made it. The same innovation that expands energy capture can collapse existing ecosystems when chemistry crosses a threshold. Progress, in biological terms, can look like self-poisoning. The tragedy is that the poison is also a signal of success. The oxygen catastrophe is a mass extinction in slow motion, and the victims were mostly invisible. Anaerobes were pushed into refuges, buried sediments, deep waters, and chemically protected niches. Some lineages adapted by inventing antioxidant defenses and new enzymes, turning oxygen from an attacker into a tool. Others survived by retreating to the few places oxygen could not easily reach. Even today, those refuges remain: mud, guts, hot springs, like living museums of an older Earth. Those defenses are not trivial because they require coordinated biochemistry. Enzymes like superoxide dismutase and catalase can neutralize reactive oxygen species, but they must be expressed at the right time and place. Membranes must be repaired, proteins refolded, DNA damage corrected before mutations accumulate. Cells also evolved redox buffers, such as glutathione systems, to keep internal chemistry within survivable bounds. The survivors were not merely lucky, they were chemically resilient in a world that was becoming less forgiving. Oxygen also rewrote nutrient cycles, and that matters for long-term habitability. Oxidation changed the solubility of metals, altered phosphorus availability, and reshaped the ocean's redox structure. It changed which metabolisms were profitable and which were impossible, because electron donors and acceptors define the energy landscape. Nitrification and denitrification become more feasible as oxygen appears, and that reshapes how fixed nitrogen moves through ecosystems. It turned the planet into a new laboratory with new constraints. Consider iron again, now as a nutrient rather than a sink. When iron precipitates out, it can become harder for some microbes to access, shifting productivity patterns. Trace metals that serve as enzyme cofactors can also change availability, quietly steering evolution. Molybdenum, for example, becomes more available under certain oxidizing conditions, influencing nitrogen fixation efficiency. In a microbial world, these shifts are not background details, they are the levers of survival. Now connect back to Oklo, because timing is not an accident. Oklo's reactors operated around 2 billion years ago, when U-235 abundance was higher. That higher enrichment was a nuclear clock set by half-lives, not by biology. Yet the planet's chemistry determined whether uranium could concentrate, whether groundwater could moderate, and whether deposits stayed stable. Even the geometry of pore spaces and the presence of neutron-absorbing impurities mattered, because physics is picky about details. The Oklo-era Earth was not only richer in U-235, it was also transitioning through oxygenation steps that changed how uranium moved through rock and water. Under oxidizing conditions, uranium becomes more soluble and mobile as uranyl complexes, and it can be carried by groundwater over long distances. Under reducing conditions, it precipitates and concentrates, often at redox boundaries where chemistry flips abruptly. Those boundaries can be thin, sharp, and persistent, natural traps created by the planet's own gradients. Oxygenation created new pathways for uranium transport and trapping, changing the odds of reactor-ready ore bodies. You can picture it as a geological conveyor belt. Oxygenated water leaches uranium from one place, Then a reducing zone captures it like a chemical net. Over time, those nets can build rich deposits, and if the geometry is right, nature can assemble a critical mass. The reactor is physics, but the setup is planetary chemistry. In that sense, the GOE is not just biology's story, but also geology's enabling condition. So the planet's impossible reactor and the planet's oxygen revolution sit in the same deep time neighbourhood. One shows nature can assemble high-energy physics without minds given patience and the right constraints. The other shows life can assemble high-energy chemistry that reshapes everything, including itself. Together, they hint at a universe where complexity can emerge, yet still be fragile. When we see an anomaly, the lesson is to ask what slow prerequisites made it possible. This is the second reframing of the Great Filter. Filters are not only external impacts and random disasters. Filters can be endogenous, produced by life, climate, and geochemical feedbacks that emerge from success. The trap is that the very act of winning can change the rules. A planet can become more energetic and more dangerous at the same time. Oxygen is the perfect double-edged gate, because it destroys and enables with the same mechanism. Oxidation is lethal to unprotected cells, yet it also unlocks far more energy per molecule of food. Aerobic respiration yields orders of magnitude more ATP than many anaerobic pathways, because oxygen is an exceptionally strong electron acceptor. That energy surplus is the budget that later pays for large bodies, fast movement, and complex nervous systems. The same molecule that corrodes metal can, in a mitochondrion, bankroll thought. But the enabling comes later, and it comes unevenly. After the germ, oxygen levels likely remained far below modern values for long intervals, perhaps a few percent or less. The planet may have oscillated, with oxygen oases and oxygen deserts, with surface waters more oxygenated than deep basins. Geological proxies suggest long plateaus where oxygen rose only slightly, then stalled as sinks reasserted themselves. Complex life needs not only oxygen, but stability in oxygen, and that stability is hard-won. This is where later oxygenation steps matter, because the GOE is not the end. The Proterozoic shows additional rises and reorganizations in ocean redox conditions, and those changes can be patchy across basins. There are intervals of widespread anoxia and euxenia, where hydrogen sulfide becomes significant in parts of the ocean. These conditions can suppress animal-friendly habitats even when some oxygen exists. A world can have oxygen in the air and still hide poison in its seas. Hydrogen sulfide is not just unpleasant, it is biologically disruptive. It binds to enzymes, interferes with respiration, and can poison ecosystems that rely on oxygen. In a stratified ocean, you can have oxygen near the surface and toxic chemistry below, separated by a thin boundary layer. That boundary becomes a moving frontier, and life must track it to survive. The frontier is also a fossil boundary, because sediments record which chemistry won at a given depth. The narrative beat is simple. Earth did not flip from dead air to modern air in one clean move. It climbed a staircase with broken steps, and each step was a gate that could have failed. If oxygen production had slowed, or sinks had reawakened, the story could have stalled for another billion years, and if it stalled, the window for later complexity might never have opened. How many planets get stuck on the wrong landing? Now bring in climate, because oxygen and climate are coupled through methane. In an anoxic world, methane can accumulate, produced by methanogens and protected by low oxygen. Methane is a powerful greenhouse gas, and it can keep a faint young sun from freezing oceans. When oxygen rises, methane is oxidized more quickly, and the greenhouse blanket thins. The atmosphere's radiative balance shifts, and the planet can cool without changing its orbit by a single meter. This creates a dangerous feedback corridor. Oxygenation can cool the planet by reducing methane, which increases ice, which raises albedo, which cools further. Cooling can slow weathering and alter nutrient delivery, which can change biological productivity and oxygen production. The system can tip, and the tip can be global. The unsettling part is that none of this requires intent, only coupled equations playing out over time. It is a reminder that habitability is not only about distance from a star, it is also about internal feedbacks that can amplify small changes into planetary transitions. A biosphere can push the climate, and the climate can push back, sometimes with brutal efficiency. In that push and pull, a world can remain stable, or fall into extremes. The Great Filter, in this view, is often a feedback loop that tightens until it snaps. Snowball Earth episodes are the extreme expression of that coupling. During parts of the Proterozoic, evidence suggests the planet may have approached near global glaciation, with ice reaching into low latitudes. Ice reflects sunlight efficiently, and once ice advances far enough, it can become self-sustaining. A frozen world is not necessarily dead, but it is a severe bottleneck for complex ecosystems. The question is not whether life can survive, but whether complexity can keep its footing. Picture the visuals: a pale planet under a dimmer sun, oceans sealed by ice, and only narrow cracks or volcanic margins offering liquid water. Katabatic winds sweep over blue-white plains, while dark volcanic ash stains the surface in streaks. Beneath the ice, chemistry continues, and microbial life can persist in refuges. Yet the surface becomes hostile to diversity, and ecological complexity is squeezed into scattered havens. The planet's biosphere becomes smaller, more isolated, and more vulnerable to chance. The key point is not to litigate every snowball detail here. The key point is that Earth's habitability is not a wide open field. It is a narrow corridor bounded by runaway greenhouse on one side and runaway ice on the other. Earth stayed in that corridor, but it did not stay there effortlessly. The corridor is maintained by feedbacks that can fail, and by timing that can be unforgiving. Oxygen sits inside that corridor as both stabilizer and destabilizer. It enables ozone formation, which shields the surface from UV and changes atmospheric structure. It also changes the oxidative weathering of continents, which affects CO2 drawdown over long timescales. Yet it can also remove methane and trigger cooling, tightening the corridor at the worst possible moment. Oxygen is not a thermostat, but it can nudge the hand that turns one. Even ozone has a dual role, because it protects surface life while also altering how energy moves through the atmosphere. A stronger ozone layer changes temperature gradients, circulation patterns, and the chemistry of other gases. These are not minor adjustments, because climate is a coupled system with many levers. When oxygen rises, it pulls several of those levers at once. The result can be stability, or it can be a new kind of volatility. So the oxygen catastrophe becomes a model great filter gate. It is a planetary transition that is hard, rare, and fragile. It requires a biosphere capable of oxygenic photosynthesis, and it requires that biosphere to persist long enough to matter. It requires sinks to saturate and burial to persist, so oxygen is not immediately consumed. It requires the planet to avoid freezing or sterilizing feedbacks during the transition. In other words, it requires success without triggering collapse. Now define filters explicitly, because the documentary needs a working map. A planetary filter is a step that must be crossed for a later outcome to be possible. It is hard because it requires unlikely innovations or rare stability across long spans. It is fragile because it can be reversed by feedbacks, extinctions, or geochemical resets. A filter is not a single obstacle, but a region of risk that must be traversed. The first filter is the origin of life, because chemistry must become heredity. Molecules must not only form but also copy with variation, so selection can begin. The next filter is persistence, because early life must survive impacts, volcanism, and ocean chemistry swings without being erased. Another filter is stable climate, because long-term liquid water needs feedbacks that do not run away. These early gates may be common or rare, but they are prerequisites for everything that follows. Another filter is oxygenation, because complex energy budgets depend on it, yet oxygenation can also kill. The gate is not simply make oxygen, but make oxygen without breaking the planet. That is a narrower requirement than it sounds, because it demands both biological innovation and geochemical timing. It also demands that ecosystems adapt quickly enough to avoid collapse. The GOE is a reminder that a planet can be alive and still fail this test. Then comes the eukaryote gate, because complex cells require endosymbiosis and internal organization. Eukaryotes change genome management, cell size, and energy distribution, because mitochondria can supply power where it is needed. They also enable multicellularity, because they can specialize and coordinate at larger scales. Multicellularity is another gate, because it requires developmental control and cooperation that resists cheating. Each gate is a new kind of coordination problem, solved only sometimes. Then comes nervous systems and complex behavior, because sensing and prediction are expensive. Intelligence is not inevitable, because it requires long lifespans, stable food webs, and selection pressures that reward cognition over simpler strategies. Then comes technological civilization, because intelligence must translate into cumulative culture, tools, and energy control. Each step is a gate, and each gate can be a graveyard. The silence we hear in the cosmos may be the sound of gates that rarely open. This is where the oxygen story loops back to the central question. If Earth had multiple filters before humans, then the absence of earlier civilizations becomes less mysterious. A planet can spend billions of years trapped behind gates, even with abundant life. The silence of deep time may reflect repeated failures, not a lack of attempts. It may also reflect worlds that never reach the oxygen threshold, remaining rich in microbes and poor in machines. Yet oxygen also complicates the question in a different way. Once oxygen enables high-energy metabolisms, it also enables faster ecological change and larger-scale engineering by organisms. It allows big bodies that reshape landscapes, alter sedimentation, and change erosion patterns. It sets the stage for any later intelligence to become a geological force. The planet becomes more editable, and therefore more vulnerable to editing. In a sense, oxygen is when biology begins to matter at planetary scale in a new way. Before oxygen, life can be widespread and still leave the atmosphere mostly unchanged. After oxygen, metabolism becomes a driver of global chemistry, and global chemistry becomes a driver of evolution. The planet and the biosphere begin to co-author the same story. That co-authorship is powerful, but it also means mistakes propagate globally. So oxygen is both prerequisite and warning. It is prerequisite because without it, complex brains are unlikely to be energetically affordable over long periods. It is warning because the first great planetary transformation driven by life was also a catastrophe. Life's success can become its own extinction mechanism, and the mechanism can be slow enough to feel inevitable. The most dangerous disasters are sometimes the ones that arrive as a gradual new normal. Now tighten the Oklo callback because it anchors our tone of disciplined mystery. Oklo shows that high-energy phenomena can be natural, and that context decides interpretation. Oxygenation shows that the planet itself can run experiments that look like design, then erase their intermediate forms. Together they suggest a world where impossible is not evidence, but a prompt to test. When we find a strange signature, we should ask what quiet processes could have built it. This chapter's gate is not a single moment, but a long chemical war. Oxygen rose, fell, and rose again, and each rise rewrote who could live where. The winners were not the strongest, but the lineages that could tolerate a changing atmosphere and a rearranging ocean. The losers may have been vast, and they left few fossils to mourn them. Their absence is itself a clue about how thoroughly chemistry can erase a world. If you could watch it from orbit, the change would not look dramatic at first. There would be no sudden flash, only subtle shifts in ocean colour, mineral deposits, and atmospheric haze. You might see coastal waters brighten with new productivity, while deeper basins darken under anoxic layering. Over millions of years, those subtleties would accumulate into a different planet. The transformation would be slow enough to be invisible, yet fast enough to be decisive. The Great Filter hypothesis often sounds like a cosmic argument about aliens. Here, it becomes a planetary argument about chemistry and time. Earth's first Great Filter was not a meteor, and not a volcano, and not a machine. It was air becoming hostile, then becoming powerful. The gate was crossed not by invention alone, but by endurance across a planet's shifting budgets. Transition to the stakes for us, because the documentary is building toward the present. If filters are gates, then passing one does not end the test. Passing one gate can create new vulnerabilities at the next gate, because new chemistry opens new failure modes. Oxygen made complex life possible, but it also made fire possible, corrosion faster, and biogeochemical cycles more tightly coupled. The same oxidizing power that fuels animals also accelerates breakdown. Fire is not just spectacle, it is a planetary reaction that becomes available when oxygen crosses a threshold. Oxidation that happens slowly in cells can happen rapidly in forests, turning stored carbon into heat and gases. Corrosion is the same story in another form, as metals and minerals are pushed toward oxidized states. Even the carbon cycle becomes more responsive, because oxygen changes how quickly organic matter can be returned to the air. Oxygen is power, but it is also an accelerating agent, so the unavoidable question returns, sharpened by deep time. If Earth had multiple filters before humans, Where does the Great Filter sit for us? Is it behind us, ahead of us, or repeating in new forms we have not recognized yet? And if it repeats, does it repeat as catastrophe, or as a quieter failure to stabilize? In a universe of gates, survival may depend on noticing which gate we are approaching. We end with the palimpsest theme, because it is the documentary's spine. Earth's record is written, erased, and rewritten by chemistry, climate, and rock. The oxygen catastrophe is one of the deepest edits, and it set the conditions for every later chapter of life. If a prior intelligence ever rose, it rose on this oxygenated stage, and it faced gates just as real. The page is never blank, but it is never permanent. Next, we follow the consequences of passing the oxygen gate into the era of complex cells and complex bodies. We ask whether complexity is a one-time accident, or a repeated attempt that usually fails, and we ask what kinds of traces, if any, could survive when the planet keeps rewriting the page. The galaxy is old, and its raw materials are common, scattered through molecular clouds like ash after a long fire. Stars like the Sun formed billions of years before Earth even cooled, and many of those stars now host planets that have had immense time to experiment. When we look up, we're not looking at a young neighbourhood. We are looking at a mature city of suns, some older, some quieter, many with histories long enough to rewrite themselves. If life and intelligence are easy, the sky should be crowded with consequences. We should see obvious engineering, loud radio leakage, and artifacts of expansion that stand out against natural astrophysics. We might expect waste heat in infrared surveys, strange spectral lines from industrial chemistry, or even the steady geometric dimming of megastructures. We might expect to catch mistakes too, accidental broadcasts, misdirected beams, or the blunt footprint of mining in a star system's dust. Instead, we see silence that feels structured, as if the universe is withholding a chapter we assumed would be inevitable. The Fermi paradox is not only a question about aliens, but about probability, timing, and the hidden difficulty of steps we take for granted. It is a mismatch between what seems possible and what appears actual. It is the uneasy gap between a galaxy that looks hospitable on paper and a sky that does not answer back. Oklo already taught the first lesson, and it was humbling in the most geological way. Nature can produce an engineered-looking anomaly, and geology can preserve it as a quiet ledger for 2 billion years. In Gabon, uranium ore once reached a concentration high enough for sustained fission, moderated by groundwater, cycling on and off like a primitive reactor. The evidence is not a rusted machine. It is a subtle depletion in uranium-235 and a pattern of fission products locked into mineral grains. So we widen the lens from one strange reactor to the whole cosmic census. If the universe is fertile, where is everybody, and why does our local sky look so unclaimed? The question is not merely whether life exists elsewhere. The question is whether complex life, technological life, and enduring life are common outcomes or rare flukes. The Great Filter hypothesis offers a brutal answer, and it does so without needing any particular alien story. Somewhere between dead matter and starfaring power, one or more steps are extremely hard, so hard that most worlds never pass them. The filter could be a single near-impossible transition. It could also be a gauntlet of moderately difficult gates that, multiplied together, become a near-zero probability. A filter can be improbability, where almost no worlds pass even once. A filter can be self-termination, where many pass briefly and then collapse before leaving durable traces. Either version can explain a quiet galaxy. Either version can also explain why we feel alone even in a universe that may be teeming with simple life. The framework is simple enough to map, and that simplicity is part of its power. Start with lifeless chemistry, then life, then complex cells, then complex bodies, then minds, then machines. Add one more implied step: persistence, because a civilization that flickers out quickly may be indistinguishable from one that never existed. Each step is a gate that must open in sequence, and each gate can be narrow in a different way. If any gate is rare or fragile, the galaxy stays quiet, even if the raw ingredients are everywhere. A single bottleneck can dominate the statistics, because the chain is only as common as its least common link. This is why the Great Filter feels so cold. It treats our existence as a data point in a probability distribution, not as a destiny. Earth gives us a timeline to test the idea, even if it cannot prove it. Our rocks show long delays between breakthroughs, and those delays are not just empty time. They are time in which the planet was chemically active, volcanically restless, and bathed in sunlight, yet still did not produce certain outcomes. The silence in the rocks is not absolute. It is selective. For most of Earth's history, there were no animals, no forests, and no firelight. There were microbes, oceans, and patient chemistry working in cycles that were stable on human scales, yet dramatic on planetary ones. If you could hover above the Archean seas, you would see a world tinted by iron, with shallow waters that could turn green or purple under microbial mats. You would see storms and tides, but no footprints on shore. Chapter 5 framed oxygenation as a planetary gate, and it deserves to be remembered as more than a single event. It was a filter that killed, enabled, and then stalled for long stretches, because oxygen is both a toxin and a tool. It reshaped minerals, altered ocean chemistry, and changed what metabolism could afford. Oxygen also built the ozone layer, which softened ultraviolet radiation and changed the surface environment. Now we ask the terrifying follow-up, and we do it with the sky still silent above us. Was the hardest gate behind us, or is the hardest gate still ahead? The question is not philosophical. It is practical, because it changes how we interpret our own future. It changes whether our existence is a triumph over improbability or a brief moment before a common failure. Begin with the filters that might be behind us, because those are the ones the rocks can at least gesture toward. The first is abiogenesis, when chemistry became heredity and selection, and when molecules began copying themselves with variation. At some point, information stopped being merely stored in patterns and began being tested by survival. That is the pivot from chemistry to evolution. We do not know how often that happens, and the uncertainty is not a small technical detail. We have one example, and we do not yet have a second planet to compare, so we cannot separate easy but rare to observe from rare in reality. Even on Earth, the earliest evidence is indirect. We infer ancient life from isotopic fractionation, from microfossils debated at the edge of microscopy, and from carbon locked in ancient rocks. If abiogenesis is rare, the silence is explained early, and it explains it cleanly. Most worlds stay sterile, and the sky stays dark. Not because life is impossible, but because the first spark almost never catches. Planets could have oceans, energy gradients, and organic molecules, yet never cross the threshold into self-sustaining evolution. In that scenario, Earth is not typical. Earth is a statistical outlier. If abiogenesis is common, the silence moves forward in the chain, and that shift changes everything. Life becomes typical, and something later becomes the bottleneck. Perhaps something we assume is inevitable because it happened here. The great filter does not disappear, it simply relocates. The next candidate is the emergence of eukaryotes, and the reason it matters is energetic as much as genetic. Complex cells may require an improbable merger, not a gradual upgrade, because large genomes and sophisticated regulation require a robust power supply. Prokaryotes can be astonishingly versatile, but their internal architecture limits how much energy they can deliver per gene. Eukaryotes break that constraint. Endosymbiosis is not just a new organelle, it is a new energy economy that can support larger genomes and tighter regulation, because mitochondria provide localized power throughout the cell. The leading picture is that an archaeal host and a bacterial partner formed a long-term symbiosis, and then the partnership became inseparable. Genes moved, membranes specialized, and the cell became a federation that could no longer live as its former parts. On Earth, eukaryotes appear late relative to life's origin, and that delay is one of the chapter's most unsettling clocks. Life arose early, perhaps within a few 100 million years after conditions stabilized, yet complex cells took far longer to arrive. That gap hints that the step might be hard, even on a living planet. It also hints that life and complexity are not the same kind of inevitability. Then comes multicellularity, which is not one invention but many, and that fact cuts both ways. It suggests that simple multicellularity may be accessible because it evolved in animals, plants, fungi, and various algae. Yet stable, complex multicellularity needs cooperation that resists cheating because individual cells can defect. Cancer is the shadow of multicellularity, and its existence tells us how fragile cooperation can be. bodies require developmental programs, cell specialization, and long-term integrity, and those are coordination problems, not only genetic ones. A multicellular organism must control growth, repair damage, and allocate resources across tissues that have competing interests. It must build an immune system to police internal threats. It must also navigate an external world that changes faster than genomes can rewrite themselves. Then comes nervous systems and behavior that can model the world, and here the filter may be about economics. Intelligence is expensive, and it demands stable energy and long lifespans because large brains consume disproportionate calories. A brain is not just tissue. It is a constant metabolic bill that must be paid every day, even when food is scarce. Earth's fossil record shows many clever animals, but only one lineage built cumulative technology that reached industry. That could be contingency, a chain of accidents and extinctions that happen to favour us. It could also be rarity, where the kind of cognition that builds machines is not a smooth extension of animal cleverness. It may require a particular combination of dexterity, social structure, and ecological opportunity. Tool use appears in several groups, and that matters, because it shows that the idea of manipulating objects is not uniquely human. Yet tools alone do not guarantee runaway culture that stacks knowledge across generations, because tool traditions can remain local and fragile. A stone used today can be forgotten tomorrow. A technique can vanish with a small population crash. Language and high-fidelity teaching change the slope, and they do so in a way that is easy to underestimate. They turn individual learning into a shared memory that compounds, allowing one generation to start where the last ended. This is not merely communication, it is compression, abstraction, and the ability to transmit invisible concepts like number, causality, and obligation. Cumulative culture is a threshold, and once crossed, a species can build on itself faster than genes can adapt. That acceleration is why technology feels like a different regime of evolution. It allows rapid exploration of design space, from agriculture to metallurgy to computation, without waiting for biological mutation. It also creates new risks, because the same speed can amplify mistakes. So one possible great filter is not intelligence in general, but the specific package that turns intelligence into a planet-shaping force. Social learning, symbolic language, and durable institutions must align, and they must persist through crises. Institutions matter because they store norms and knowledge outside any one brain. They are cultural memory made structural. If that package is rare, then earlier Earth civilizations become unlikely, and the silence in the strata is less mysterious. The planet might host many minds, yet never host machines, because minds alone do not guarantee metallurgy, writing, or energy-intensive industry. Intelligence could remain ecological rather than technological. A world could be full of awareness and still never build a radio. But the documentary's premise keeps pressure on the map, because Earth is not only a case study, it is a testbed for our assumptions about detectability and deep time. If intelligence can arise, could it arise more than once on the same planet, separated by extinctions and resets? Could evolution roll the dice again and again, and occasionally land on something like us? This is the repeated rise scenario, and it sits at the edge of what the fossil record can answer. Intelligence could be convergent, emerging wherever brains pay off in complex environments, or it could be a near accident dependent on a narrow path. Convergence is the idea that similar problems produce similar solutions, like eyes evolving multiple times. Accident is the idea that some outcomes require a specific chain of contingencies. The fossil record offers hints, but it is not a full camera, and the limitations are not trivial. Soft tissue rarely preserves, and cognition leaves indirect traces, which means the most relevant evidence is often missing. We can see bones, shells, and teeth. We cannot directly see planning depth, theory of mind, or the richness of communication. We can see eyes, hands, and skulls, and we can infer sensory priorities from anatomy. We can infer locomotion from joints, and diet from teeth, and sometimes social behavior from trackways. Yet inference has limits, because a brain's computational style is not fossilized. A large brain case suggests capacity, but it does not guarantee culture. A clever animal can still live in a world with no cumulative tradition. We can also miss entire lineages in gaps, and those gaps are not evenly distributed across time. Preservation is uneven, and deep time is a biased sample of what once lived, filtered by sedimentation, erosion, and chance discovery. Whole ecosystems can vanish without leaving a clear archive. Even when fossils exist, they may be inaccessible, buried deep or destroyed by metamorphism. Still, the record is suggestive in a cautious way, and caution is part of the scientific posture. Complex animals appear late, and technological behaviour appears extremely late, almost at the last moment of the timeline. That pattern can be read as a filter behind us, implying that the ladder is hard to climb. It can also be read as a warning about how long it takes to reach the edge, even when conditions are favourable. Now shift to the filters that might be ahead of us, because these are the steps after a species gains planetary scale power. A technological civilization can become its own asteroid, not in mass, but in impact. It can change climate, chemistry and biosphere faster than feedbacks can stabilise. It can turn slow geologic cycles into fast human cycles. Runaway climate change is a candidate filter, and it is not only warming in the simple sense, it is cascading shifts in oceans, ice and carbon sinks, where one change triggers another, and the system moves to a new equilibrium. Warmer oceans hold less dissolved gas, which affects oxygen and marine life. Melting ice changes albedo, which changes how much sunlight is absorbed. Thawing permafrost can release additional greenhouse gases, adding momentum to the shift. Resource overshoot is another candidate, and it is older than industrial society as a concept. A society can consume its foundations, then discover limits only after resilience is gone. Because depletion often looks like prosperity at first, the danger is not running out of a single material. The danger is destabilizing the networks that deliver food, energy, and trust. Loss of biodiversity is not just moral loss, and it is not only about charismatic species. It is the collapse of ecosystem services that stabilize food webs and climate buffers, including pollination, soil formation, and nutrient cycling. Biodiversity is also a form of redundancy, and redundancy is what keeps systems functioning when stressed. When redundancy is stripped away, shocks become collapses. Nuclear war is the obvious hard edge, and it carries both immediate and long-tail consequences. It is a fast pathway to mass death, infrastructure loss, and long recovery under poisoned trust, because survivors inherit a world shaped by fear and scarcity. Beyond blast and radiation, there is the risk of nuclear winter, where soot injected into the stratosphere cools the planet and disrupts agriculture. Even a limited exchange could ripple through global food systems. Engineered pandemics add a quieter edge, and quiet is part of what makes them frightening. Biotechnology scales cheaply, and mistakes can outrun containment, especially when incentives reward speed. A pathogen does not need malice to become catastrophic. It needs transmissibility, immune evasion, and a world connected by travel. AI misalignment is a newer candidate filter, and it is difficult because it is conceptual as well as technical. It is the risk of building optimization that does not share human values or constraints, then giving it access to critical systems. The danger is not science fiction robots. The danger is systems that pursue goals with relentless competence, using resources we cannot revoke. Misalignment is also hard because it can hide behind apparent success. A system can look helpful while it is still weak, then become unmanageable when it is strong. It can exploit loopholes in objectives, because objectives are never complete descriptions of what we mean. The great filter, in this framing, is not a meteor. It is a mismatch between capability and control. Stagnation traps are a different kind of filter, and they are easy to overlook because they do not look like disaster. A civilization can survive, yet never expand, never signal, and never leave durable traces, because it settles into a stable equilibrium. Stagnation can be political, ecological, or psychological. It can also be a deliberate choice, where a society prioritizes stability over growth. From the outside, stagnation and extinction can look similar, because both produce silence. A civilization that turns inward might minimize energy use, reduce emissions, and avoid detectable beacons. It might communicate through tight beams or local networks that do not leak into space. It might also exist mostly in environments we do not easily observe, like subsurface habitats or digitally mediated worlds with low physical footprint. These forward filters change how we interpret the cosmic quiet, because they add a second explanation beyond rarity. The silence could mean nobody gets far, or nobody stays loud, or that loudness is a brief developmental phase. Perhaps civilizations are most detectable during a short, wasteful adolescence. Perhaps maturity looks like invisibility. Now tie this back to Earth's deep past. because the documentary's central tension lives here. If advanced civilizations rose before humans, they face the same forward filters, and they face them without our hindsight. Either they were filtered out quickly, leaving little time to spread, or they persisted quietly, leaving traces below our detection threshold. Chapter 2 explained why traces are hard to keep, and the mechanism is relentless. Plate tectonics, metamorphism, and burial can shred even durable engineering, turning cities into sediments and sediments into rock. Continents move, oceans open and close, and mountain ranges rise where seabeds once lay. The planet is not an archive built for us. It is a machine that recycles its own pages. Chapter 3 explained why chemistry is both powerful and treacherous, and Oklo is the perfect emblem. Isotopes can be ledgers, but nature can counterfeit signatures, because physics and geology can produce patterns that resemble intention. A nuclear-like pattern can be natural, and a real pattern can be erased into ambiguity. The same processes that preserve can also blur, so the great filter becomes a double suspense, and that double layer is part of the chapter's mystery. It is a filter on survival, and it is also a filter on evidence, because even if something happened, it may not remain readable. A prior civilization could fail, and the planet could clean up, leaving a world that looks like ours, with no obvious scars. The absence of evidence becomes ambiguous rather than decisive. That possibility does not prove anything, and it cannot be used as a shortcut to extraordinary claims. It only widens the space of what could be true, given Earth's recycling and our limited sampling of deep time. We have drilled only tiny punctures into the crust. We have mapped only parts of the seafloor at high resolution. We have not read the whole book. Scientific humility matters here, because the great filter is not a mechanism we can point to in a rock layer. It is a framework for reasoning under uncertainty, a way to organize ignorance and ask sharper questions. We can use it to ask better questions. We cannot use it to claim that a particular extinction was engineered without decisive markers. Existential risk reasoning is about plausible pathways, not about historical proof, and that distinction keeps the narrative honest. It is a map of vulnerabilities, not a record of past crimes. It asks what could go wrong when a species gains power faster than it gains wisdom. It also asks what kinds of mistakes are likely to repeat, because repeating mistakes is what evolution and history often do. Still, the framework sharpens the central question, and it does so with uncomfortable clarity. Are humans the first technological intelligence on Earth, or just the latest attempt, arriving after others failed? If we are first, then one of the hardest filters may be behind us, and the silence in the galaxy might be explained by rarity. That is comforting, but it also makes our rarity feel heavy, because it implies responsibility without precedent. If we are not first, then the filter may be ahead of us, and the implication is darker. It would suggest repeated failure after reaching power, a pattern of civilizations that ignite and then extinguish. It would suggest that intelligence is not the finish line. It is the moment the real test begins. Either way, the great filter points toward the same edge, and the edge is narrow. Intelligence may be fragile, and progress may be a corridor with steep walls. The corridor may be bounded by physics, by ecology, and by psychology. The question becomes whether we can stay inside it. Now return to the repeated rise scenario with stricter logic, because it is easy to drift into storytelling. If intelligence is convergent, then Earth should have produced multiple near misses, especially over hundreds of millions of years with diverse ecosystems. Near misses might look like sophisticated tool use without industry. They might look like cultural complexity without fossilizable infrastructure. They might look like long-lived societies that never cross into high-energy technology. If intelligence is a rare accident, then the absence of earlier techno-signatures is expected, and the story becomes simpler. The planet may simply have never rolled the right dice until now, because the path required a specific sequence of events. Mass extinctions reset ecosystems and open niches, but they also erase experiments. Continental drift reshapes climate and geography, changing the selection pressures that favour certain traits. The fossil record cannot settle this alone, and it is important to say why without dismissing its value. It can show morphology and ecology, but it cannot show the full space of cognition, because cognition is behaviour over time. A species could be intelligent in ways that leave no durable mark. It could communicate richly without writing. It could build with perishable materials in environments that do not preserve. So we need a different kind of test, And this is where the chapter turns from philosophy toward measurement. We need to ask what a technological interval would do to sediments, ice and stone, because geology records chemistry more reliably than it records architecture. A civilization is not only artifacts on the surface, it is altered cycles of carbon, nitrogen, metals, and radionuclides. It is combustion residues, industrial particulates, and mining signatures distributed by wind and water into layers that can become a global timestamp. It is an abrupt coupling of anomalies that move beyond local geology, because industry tends to synchronize signals across continents. When humans burn fossil carbon, we do not merely emit CO2, we shift isotope ratios, change ocean acidity, and redistribute nitrogen through fertilizers. Even without naming specific modern markers, the principle is clear. Technology concentrates, separates, and transports elements at rates that natural systems rarely match. It produces sharp gradients, novel compounds, and global dispersal of fine particles. It also tends to create multiple signals at once. Carbon shifts alongside metal spikes, soot alongside nitrogen changes, and unusual sedimentation patterns near coasts. But Oklo warns again, because nature can mimic parts of that suite, and it can do so convincingly. Volcanism can spike metals and aerosols, and large igneous provinces can drive climate change through massive CO2 release. Impacts can spike iridium and produce soot from global fires. Anoxia can shift isotopes by changing biological productivity and ocean chemistry. Nature has its own repertoire of abrupt coupled events, so any claim must be multi-signal and context-aware, and this is where rigor becomes the story. It must show patterns that natural processes struggle to reproduce together, in the same layer with the same timing. It must also fit the sedimentary context, because a true signal should appear where deposition would capture it. A single anomaly is a hint, a coherent suite is a case. This is where the great filter connects to method, and the connection is tighter than it first appears. If filters erase civilizations, then our detection threshold becomes part of the story, because we may be looking for signatures that cannot survive. A short-lived civilization might leave a thin, smeared boundary, later mixed by burrowing organisms, currents, and chemical diffusion. A long-lived one might leave a clearer global fingerprint if it reached scale and persisted through multiple depositional cycles. We also have to admit a hard limit, and admitting limits is not pessimism. Many industrial molecules decay, many isotopes have short half-lives, and deep time erases the loudest clues, especially in active crust. Oceanic crust is recycled on timescales of hundreds of millions of years, which means seafloor archives are often temporary. Surface landscapes erode and rivers carry their evidence away. That does not make the search pointless, and it does not make the question unscientific. It forces us to focus on the few signatures that can survive, and on redundancy across archives, because redundancy is how science builds confidence. If a signal appears in marine sediments, continental lakes and ice cores, it is harder to dismiss. If it appears only in one quarry, it is easier to doubt, so the suspense becomes practical, and practicality is what turns mystery into investigation. If earlier technological species existed, what would we actually measure to find them, and where would we look? We would look for carbon isotope excursions that match rapid fossil carbon release, paired with soot, metals, and unusual nitrogen patterns. We would look for changes in sedimentation rates that indicate altered land use, erosion, or coastal engineering. We would look for abrupt shifts that are global rather than regional. We would look for persistent synthetic-like halogen anomalies, if any can survive burial, and we would treat them as clues rather than trophies. We would look for fly ash spheres and combustion residues, because high-temperature combustion produces distinctive particles. We would look for unusual distributions of heavy metals that suggest large-scale extraction and dispersal. We would also look for patterns consistent with agriculture, such as widespread nutrient redistribution. We would look for radionuclide patterns that resist natural explanations, while ruling out Oklo-like reactors through geology and isotope suites. Natural reactors require specific conditions, including uranium concentration, water moderation, and geochemical containment. A technological nuclear signature would likely show different ratios, different spatial patterns, and different associations with other industrial markers. The goal would not be to find a single smoking gun. The goal would be to find a fingerprint with multiple ridges. We would also look for timing that makes sense, because timing is part of causality. A technosignature should align with rapid environmental change, not drift randomly through strata, and it should show a coherent onset and decline. If a civilization rose and fell, the signal might resemble a pulse. If it persisted, the signal might resemble a plateau with internal structure. But we must keep the humility line bright, because the temptation to overread is strong when the question is dramatic. These are hypotheses about fingerprints, not confirmations that fingerprints exist. The Great Filter is compelling because it explains silence without assuming we're alone. It is terrifying because it implies a common failure mode, and because it makes our future feel statistically constrained. It also reframes Oklo one more time, and the reframing is the chapter's quiet refrain. Nature can build a reactor, and nature can erase a civilization, leaving only accounting traces that are easy to misinterpret. Earth's past is a palimpsest, and our instruments read faint ink, sometimes through layers of later writing. The question is whether any earlier writing remains legible, and whether we would recognize it if it did. Now we pivot toward the next task. Frameworks need tests, and tests need targets that geology can preserve, because speculation alone cannot carry the weight of this question. If earlier technological species existed, their most durable fingerprints should be chemical and stratigraphic, not architectural, and they should be detectable as patterns rather than monuments. So the next chapter asks a narrower, measurable question. What signatures would survive in sediments, ice and stone, and how close are we to detecting them? Oklo is our warning label. Nature can fake intention, and geology can hide it for ages. It reminds us that artifacts are not always bolts and bricks. Sometimes they are ratios, textures and anomalies that only make sense in context. So we stop asking what artifacts look like, and ask what industry does to cycles. We ask what it does to the planet's bookkeeping, because cycles are where the receipts accumulate. This chapter is the calibration test. If humans vanish tonight, what would Earth remember in 10 million years? Imagine the lights going out across continents, and then the slow return of weather, roots, and rivers. The immediate ruins would be obvious to a drone, but not to deep time. Deep time does not see skylines. It sees layers, minerals, and isotope curves. Start with the Anthropocene as an uncontrolled experiment, because it is already in the rocks. It is uncontrolled because no single lab designed it, and no ethics board approved it. It is an experiment because it perturbs boundary conditions, then watches the system respond. We change the atmosphere, the oceans, and the biosphere fast enough to matter. The key word is fast. Rates can be as diagnostic as magnitudes. Carbon comes first because it is global, measurable, and tied to energy. Carbon is also the core of life's chemistry, so it moves through air, water, and organisms. Fossil carbon is old carbon, and burning it shifts the carbon budget abruptly. In simple terms, we are moving carbon from rocks to air in a geological instant. That transfer is not subtle when it happens in centuries rather than millennia. CO2 rises as a concentration spike, but the deeper marker is isotopic. Fossil fuels are depleted in carbon-13, so D13C trends negative. That depletion comes from photosynthesis, which prefers the lighter carbon-12. Over time, buried organic matter locks in that light signature, and combustion releases it again. The atmosphere does not just get more carbon, it gets a different kind of carbon. That shift is not just air. It propagates into ocean-dissolved inorganic carbon, shells, soils, and organic matter that later becomes sediment. The ocean absorbs CO2, then equilibrates it with bicarbonate and carbonate ions. Plankton build calcium carbonate shells from that pool, and their chemistry becomes a time capsule. So a change in the sky can become a change in limestone. The signal can be traced from air bubbles to seafloor mud if the archive remains intact. Methane is trickier because it is episodic and chemically active. It oxidizes to CO2, it reacts through atmospheric chemistry, and it varies with wetlands and temperature. Yet a sustained methane rise can leave coupled signals in carbon isotopes and climate proxies. Methane from biological sources is often very light in carbon-13, which can deepen a negative excursion. It can also amplify warming, which then alters rainfall, erosion, and vegetation. One molecule can tug on many threads. When methane spikes, the planet's response can be non-linear. Warming can expand wetlands, which emit more methane, which warms more. In ice cores, methane jumps are sharp, but ice is a young archive. In rock, we look for indirect echoes, changes in leaf wax isotopes, shifts in pollen, and temperature proxies that move in step. The question is whether those echoes align with other industrial fingerprints. A methane story alone can still be a natural story. The nitrogen cycle is a second ledger, and it is harder for nature to counterfeit in the same way. Nitrogen is abundant in the air, but most life cannot use N2 directly. For most of history, biology relied on specialized microbes and lightning to fix nitrogen. Industrial fixation changed that constraint, turning atmospheric nitrogen into fertilizer at enormous scale. That redistribution changes the planet's reactive nitrogen inventory, not just its location. Industrial fixation and fertilizers move reactive nitrogen at planetary scale. The Haber-Bosch process, developed in the early 20th century, made ammonia from N2 and hydrogen under high pressure. It was a triumph of chemistry and a pivot in human history. It fed billions, and it also rewired ecosystems. The same molecule that grows crops also leaks into rivers, coasts, and the atmosphere. That redistribution changes D15N patterns in sediments, lakes, and coastal margins. It also drives eutrophication, anoxia, and altered burial of organic carbon. Excess nutrients trigger blooms, and blooms eventually decay, consuming oxygen. In shallow seas, that can create dead zones where fish vanish and sediments turn dark. Those dark layers can preserve organic matter differently, changing what gets buried and what gets recycled. So nitrogen becomes a geological actor, not just an agricultural input. Ocean acidification is the third global consequence because CO2 becomes chemistry. When CO2 dissolves in seawater, it forms carbonic acid, which dissociates and lowers pH. Lower pH changes carbonate saturation, which changes where shells dissolve. The ocean is buffered, but buffering has limits, especially when the input is fast. In plain terms, we're making it harder for many organisms to build and keep shells. In sediments, that can appear as dissolution horizons and shifts in carbonate accumulation. It can also reorder microfossil assemblages in ways that track acidity. Foraminifera and coccolithophores are tiny, but they are prolific, and their shells rain down continuously. A subtle change in shell thickness, species composition, or preservation can mark a chemical transition. The seafloor can record a kind of invisible corrosion written in missing carbonate. Now add the physical debris of industry, because some of it is geologically weird. Plastics, concrete, fly ash, and novel alloys are not subtle. They are materials optimized for human timescales, not for tectonic ones. Their novelty is not only composition, but also distribution. Nature makes polymers, but not usually in global, uniform scatter. Plastics are everywhere, but their deep time survival is conditional. Sunlight and oxygen break them down quickly on the surface, then burial changes the game. On beaches, ultraviolet light embrittles polymers, and waves grind them into fragments. In soils, microbes and oxidation can chew at them, though slowly. Once buried, oxygen drops, temperatures rise and chemistry shifts. The same bag can become a different substance depending on where it ends up. In anoxic sediments, fragments can persist longer, but heat and pressure eventually polymerize, crack, or metamorphose them into carbon-rich residues. Over time, polymers can cross-link, losing their original structure. Under deeper burial, they can break into smaller hydrocarbons or become a thin film of altered carbon. The end state may resemble natural kerogen, which is why identity can fade. The plastic may survive as carbon, but not as plastic. Microplastics can become a stratigraphic marker in the near term. They can be trapped in lake muds, deep sea clays, and even polar snow. Their shapes, fibers, beads, and jagged shards can be distinctive under a microscope. Over hundreds of millions of years, they may lose identity, leaving only altered organics. That raises a question that haunts this chapter. Is a marker still a marker if it becomes chemically ordinary? Concrete is a human rock, but it is also chemically unstable. It cracks, carbonates, and dissolves, then becomes calcium-rich rubble that blends into sediment. Cement hydrates are not eternal minerals, and water finds every weakness. Carbonation turns calcium hydroxide into calcium carbonate, changing strength and chemistry. Rebar rust expands, splitting the matrix from within. What looks permanent to us is, to geology, a reactive paste. Yet the scale matters. Cities and roads concentrate carbonate minerals and rebar corrosion products in patterns that are spatially unnatural. Even if individual buildings vanish, the aggregate can form thick horizons of rubble. Those horizons can include glass, brick, and metal oxides mixed in unusual proportions. In aerial view, a metropolis is a pattern. In stratigraphy, it can become a lens of mixed minerals. The question becomes whether that lens survives burial without being reworked beyond recognition. Fly ash is a sharper candidate because it is born in high-temperature combustion. Coal ash forms glassy spheres and magnetic grains that settle globally. In power plant boilers, minerals melt and quench into tiny beads. Those beads can travel far in the atmosphere, then drift down onto oceans and continents. Under a microscope, they can look like alien pollen, perfect spheres with smooth skins and hollow interiors. Those spheres can survive burial as distinctive microfossil-like particles. Their chemistry can carry trace elements that point back to combustion conditions. Some contain iron-rich phases that respond to magnets, making them easy to separate. Others carry signatures of cold geology and burning temperature. A layer enriched in these particles can be thin, widespread, and time-specific. That combination is exactly what stratigraphers crave. Heavy metals are another industrial fingerprint because we mine and disperse them. Lead, mercury, copper, chromium, and nickel shift from ores into air and water. In nature, these elements are often locked in sulfides and silicates. Mining breaks that lock, and smelting volatilizes and redistributes metals. The result is not just more metal, but more mobile metal. Sediments near coasts and rivers can record spikes in these metals. The key is not a single metal, but a coordinated enrichment pattern. Lead might rise with zinc and copper, while mercury tracks combustion and atmospheric transport. Isotopes can add another layer, because ores have characteristic isotope ratios. If the ratios match known ore provinces, the story becomes more constrained. A fingerprint is strongest when it has multiple ridges. We also moved species across the planet, and that is a biological technosignature. Rats, crops, pathogens, and invasive plants create sudden biogeographic mixing. For millions of years, oceans and mountains separated lineages, and evolution wrote regional dialects into life. Global trade erased many of those barriers in a few centuries. The biosphere became more homogenized, even as local diversity often declined. That is a strange kind of signature, absence and mixing at once. In the fossil record, that looks like abrupt range expansions and homogenization. It can also look like extinction pulses tied to habitat disruption. Some extinctions are loud, like the end Cretaceous, but others are quieter and selective. Human-driven change can remove large animals first, then ripple through food webs. Pollen records can show forests replaced by crops, then secondary growth. The archive can record not only death, but replacement. Now, we ask the time question directly, because deep time is the enemy of certainty. What survives at 10 million years is not what survives at 1 billion. The planet is not a library with climate control. It is a working machine that heats, squeezes, dissolves, and recycles. Every marker we propose must run a gauntlet of erosion, burial, diagenesis, and tectonics. At 10 million years, many Anthropocene markers remain crisp in sediments. Isotope shifts, fly ash, metal spikes, and species turnovers can still be resolved. Many sedimentary basins will still be relatively shallow, and minerals will be only mildly altered. The layers can be correlated, and the signals can be measured with modern instruments. 10 million years is long for us, but short for rock. At 100 million years, plate motion and burial complicate the archive. Ocean crust is mostly gone, and many coastal sediments are subducted or uplifted. Diagenesis turns soft mud into shale, and pore waters can move elements around. Heat can reset some isotopic systems, and pressure can erase delicate textures. The record becomes patchier, and correlation becomes harder. We're no longer reading a continuous diary. We're reading surviving pages. At 1 billion years, metamorphism and recycling dominate. Only the most stable regions preserve readable layers, and even there diffusion blurs fine detail. Minerals recrystallize, and original pore spaces vanish. Isotopes can exchange, especially if fluids circulate during mountain building. The best we can hope for is a few preserved basins on ancient continental cores. The signal, if it exists, must be robust to transformation, so we narrow to long-lived stratigraphic markers. the ones that behave like accounting entries. Stable isotope shifts can persist when rocks stay closed systems. Carbonates can preserve carbon isotope ratios through long spans if they avoid high-grade metamorphism. Organic carbon can also preserve isotopic anomalies, though it is more reactive. The key is not immortality, but survivability under plausible histories. Carbon-13 excursions are common in Earth history, so they are not proof. The question becomes whether the excursion is paired with other industrial proxies. Earth has seen massive volcanism, methane hydrate releases, and shifts in productivity that move D13C. Many of those events also cause extinctions and ocean anoxia, so carbon alone is an alarm, not an identification. We need corroboration that points away from purely natural drivers. Abrupt sediment changes are another candidate, because humans accelerate erosion. Deforestation, agriculture, and construction increase sediment flux into deltas and shelves. When vegetation is removed, soils loosen, and rivers carry more load. Dams complicate the picture, trapping sediment upstream while starving deltas downstream. The net effect is spatially complex but often rapid. A sediment pulse can be a signature of land use change if we can rule out climate alone. That can create distinctive grain-size shifts and rapid deposition pulses. Yet floods and glaciations can do similar things, so context is mandatory. Grain size, mineralogy, and pollen can help separate mechanisms. A flood deposits a pulse, but it may not bring fly ash spheres or fertilizer-like nitrogen signals. A glaciation leaves telltale dropstones and striated clasts. The story becomes stronger when multiple lines agree. Radionuclide fallout is the most cinematic marker, but it has a half-life problem. Many bomb isotopes decay quickly on geological timescales. The mid-20th century produced a global pulse of artificial radionuclides spread by the stratosphere. It is nearly synchronous, which is rare in geology. Yet synchrony is not enough if the atoms vanish. Deep time does not care about our dates, only about half-lives. Still, fallout creates a distinctive, globally synchronous layer. Plutonium isotopes, cesium, and unusual actinide ratios form a narrow timestamp. Some isotopes bind to clays and organic matter, which can help preserve them. Others migrate with water, smearing the signal. The best archives are often quiet basins with fine sediment and low oxygen. In such places, a thin layer can remain surprisingly coherent. At 10 million years, much of that stamp is still detectable with sensitive mass spectrometry. At 100 million years, only longer-lived isotopes remain. Plutonium-239 has a half-life of about 24,000 years, so it fades quickly in deep time, but some decay products and longer-lived actinides can persist. The signal becomes less like a bright line and more like a subtle anomaly. Detectability becomes an engineering problem for future scientists. At 1 billion years, most anthropogenic radionuclides are gone, unless trapped in exceptionally stable minerals. The signal becomes a faint memory, not a beacon. If radionuclides are incorporated into zircon or other resistant phases, they can be sheltered, but that requires specific conditions, and it cannot be assumed globally. The most likely outcome is that the nuclear layer becomes a ghost of a ghost. It is still conceptually powerful, even if it is physically fragile. Industrial metals can outlast radionuclides because they do not decay. They move, though, and groundwater can smear them across layers. Metals can be adsorbed, precipitated, or dissolved depending on redox conditions. A changing water table can redistribute them long after deposition. That mobility is a problem for sharp stratigraphy. Yet mobility can also create halos that point back to a source. So the marker is not just concentration, but stratigraphic geometry and co-occurrence. A thin global metal spike is harder to explain naturally. A broad smeared enrichment could be a hydrothermal overprint or a diagenetic front. Geometry matters because processes have shapes, and shapes can be diagnostic. Co-occurrence matters because independent processes rarely synchronize perfectly. We are looking for improbable alignments. Now we confront the nuclear question with Oklo as the reference case. Oklo proves fission signatures can be natural, and that forces stricter criteria. 2 billion years ago, uranium-235 was more abundant because it decays faster than uranium-238. Groundwater, concentrated uranium in porous sandstone, and a natural reactor went critical. The physics is ordinary, even if the outcome feels uncanny. Oklo is the reminder that impossible is often just unfamiliar. Weapons testing differs from reactors in isotopic patterns and distribution. Tests spread a global aerosol signature, while reactors concentrate waste locally. A bomb produces a brief intense neutron flux and a characteristic suite of products. A reactor produces sustained fission and neutron capture, with different ratios and burn-up patterns. The distribution also differs, because bombs loft material into the atmosphere. Reactors, by design, keep material inside systems until they fail or are dismantled. Reactor operations create specific fission product suites and neutron capture products. They also create engineered isotopic ratios in uranium and plutonium. Fuel enrichment changes the starting composition, and burn-up changes the ending composition. Neutron capture creates isotopes that are rare in nature at those abundances. Spent fuel contains a complex mixture, including neodymium, cesium, strontium, and various actinides. In principle, that mixture can be diagnostic if it is preserved. Oklow's persuasive power comes from its internal consistency. Depleted U-235, fission product neodymium yields, and xenon isotopes align with reactor physics. The xenon is especially telling because noble gases can be trapped in minerals and preserve isotopic ratios. The pattern matches what we expect from fission, not from ordinary decay. Oklo is not one clue, but a converging bundle. That is why it is such a powerful calibration point. So what would distinguish an engineered reactor from a natural one? Enrichment patterns would be the first clue, because technology separates isotopes deliberately. Natural uranium enrichment is limited by geology and half-lives. Engineered fuel can show sharp U-235 or Pu-239 signatures that do not fit or formation. The sharpness matters, because nature tends to grade and mix. Engineering tends to produce discrete batches and boundaries. Waste distributions would be the second clue, because engineering concentrates and packages. A reactor site could show localized, layered waste minerals and containment materials. Even if containers corrode, the initial geometry may leave a pattern in the surrounding rock. Think of it as a chemical shadow of an engineered layout. Natural reactors are controlled by permeability and ore bodies, not by design. Their products should follow geology, not architecture. Associated materials would be the third clue, because reactors are systems. Corrosion products, structural alloys, concrete residues, and unusual ceramics could co-occur. Zirconia, boron compounds, and specialized steels are not common in natural ore settings. Even if they degrade, they can leave unusual elemental associations. The presence of multiple engineered materials in one stratigraphic context would be hard to dismiss. It would not be a smoking gun, but it would be a strong smell. Yet deep time punishes complexity. Metals corrode, ceramics fracture, and the system collapses into a geochemical halo that can look like ore alteration. Fluids move through fractures, carrying elements away from their original positions. Redox fronts can precipitate uranium and mimic waste concentration. The longer the time, the more the site becomes a blurred stain. That is why Oklo is both encouraging and sobering. So the nuclear techno-signature must be multi-isotope and multi-material. It must show patterns that are hard to generate by groundwater and redox fronts. We would want consistent fission yields across multiple elements, not just one. We would want isotopic ratios that match engineered enrichment rather than natural abundance. We would want spatial patterns that imply discrete operations rather than diffuse geology. In other words, we would want a story that stays coherent under hostile scrutiny. Now widen beyond chemistry to geomorphology, because civilization reshapes landscapes. Mining moves rock volumes fast, leaving pits, tailings, and altered drainage. From above, open pits are geometric wounds, and tailings ponds are unnatural mirrors. Waste rock piles have slopes that betray bulldozers rather than gravity. Rivers are diverted, channels straightened, and valleys filled. The landscape becomes a machine for moving material, but landscapes heal faster than we want to believe. Erosion fills pits, rivers reroute, vegetation returns, and the scars become subtle topography. Freeze-thaw breaks walls and landslides soften edges. Sediment blankets the sharpest forms, and soils develop over rubble. In a few thousand years, many features become ambiguous. In a million, they can become just another hill. On million-year timescales, even large mines can be buried or eroded flat. The most durable geomorphic signals are those that change sediment routing at scale. If a basin receives a sustained pulse of sediment from disturbed land, that can persist as a stratigraphic package. If a river is permanently rerouted, it can reshape deltas and coastal deposits. Geomorphology survives best when it becomes stratigraphy. The landform must translate into a layer. Subduction is the brutal eraser for ocean floor evidence. Most seafloor is recycled within 200 million years, taking coastal cities and ports with it. The ocean floor is young because it is constantly created at ridges and destroyed at trenches. Any industrial layer on the seabed has a built-in expiration date. Even thick sediment can be scraped, folded, and metamorphosed in subduction zones. The sea is a poor, long-term archive, despite its vastness. That is why continental cratons are the best bet for ancient technosignatures. They're old, stable, and less likely to be cooked beyond recognition. Cratons have survived multiple supercontinents, collisions, and rifts. Their interiors can preserve basins that remain relatively cool. They can hold sediments that are hundreds of millions, even billions of years old. If anything is going to survive, it will survive there. Cratons preserve ancient sediments, paleosols, and basin fills that can hold chemical anomalies. They also preserve long stratigraphic continuity across deep time. Paleosols are fossil soils, and they can record atmospheric composition and weathering intensity. Basin fills can record long environmental histories with minimal interruption. In such sequences, a thin anomalous layer can be bracketed and dated. The archive is not perfect, but it is legible. Yet even cratons are not perfect archives. Intrusions, metamorphic events, and groundwater can reset isotopes and redistribute elements. A dike intrusion can heat surrounding rock and mobilize fluids. A distant mountain building event can send pressure waves and metamorphic gradients. Even slow groundwater flow can alter minerals over long periods. Stability is relative, not absolute. So the search becomes a signal-to-noise problem, not a treasure hunt. Nature produces spikes, excursions, and anomalies that can mimic industry. Earth is not a quiet baseline interrupted only by humans. It is a restless planet with its own catastrophes and pulses. If we want to detect ghost industries, we must first respect the planet's ability to surprise us. The noise is not random, it is structured by geology. Volcanism can raise CO2 and shift D13C through massive carbon release. It can also deposit mercury, sulfur aerosols, and ash that look industrial. Large igneous provinces erupt over thousands of years, injecting gases and particles. They can trigger warming, acid rain, and ocean anoxia. Mercury spikes in sediments are often linked to such events. If we see mercury and carbon shifts together, volcanism becomes a strong alternative hypothesis. Impacts can create soot layers, iridium spikes, and abrupt extinctions. They can also trigger wildfires and climate shocks that resemble human forcing. A bolide strike can loft dust, darken skies, and cool the planet quickly. It can ignite global fires, leaving charcoal and soot. The iridium anomaly is a classic marker, but not the only one. Impacts can mimic some aspects of industrial disruption, though their timing and mineralogy differ. Natural hydrocarbon seeps can release methane and lighter carbon, shifting isotopes locally. Organic-rich basins can create metal enrichments without any machines. Reducing conditions can concentrate uranium and other metals in black shales. Sulfide formation can trap metals and create spikes. Methane can seep along faults and alter nearby carbonates. Nature can assemble pieces of our signature, just not always in our combination. Oklo itself is the cautionary tale inside the cautionary tale. A natural reactor can produce fission products that look engineered, unless context is nailed down. If we found Oklo without knowing its geology, we might tell the wrong story. That is the lesson. Anomaly is not attribution. Context is the difference between a mystery and a conclusion. The rocks demand humility, so a strong case requires multiple independent proxies that converge. Carbon isotopes alone are weak, metals alone are weak, and radionuclides alone decay away. The target is an anomalous combination that is hard to assemble naturally. We want signals that arise from different processes, yet align in time. We want chemistry, biology, and particles telling the same story. Convergence is the closest thing geology has to certainty. A rapid D13C shift paired with fly ash spheres and fertilizer-like D15N changes. Add heavy metal enrichment with industrial ratios, plus microfossil community disruption consistent with acidification. Then the pattern starts to resist natural stories. It begins to look less like a single catastrophe, and more like a systemic perturbation. It suggests energy use, land use, and chemical redistribution happening together. That is what industry does. It couples domains. Even then, we must test alternative mechanisms aggressively. Could a flood basalt event plus wildfires plus anoxia reproduce the same suite? Could unusual sediment focusing concentrate fly ash-like particles from a single region? Could diagenesis create apparent isotope shifts by altering carbonates after burial? Each proxy has failure modes, and each must be stress-tested. The goal is not to win a narrative, but to survive cross-examination. This is where measurement strategy matters more than narrative desire. We need precision, replication, and geological plausibility across multiple basins. Precision because small shifts can be meaningful, but also because noise can masquerade as signal. Replication because one core can be contaminated, reworked, or misdated. Plausibility because geology has constraints, and we must obey them. A good hypothesis is one that risks being wrong. Practical searches start with where preservation is best. Targeted drilling in ancient stable regions can sample continuous sediments with minimal metamorphism. Drill cores are not cinematic, but they are honest. They pull up time as a cylinder, layer by layer, without the bias of surface exposure. In a core, the boundary layers are protected from weathering. The archive is still incomplete, but it is less edited. High-precision isotope surveys can scan for abrupt excursions in D13C, D15N, and trace metal isotopes. The goal is to find candidates, not conclusions. Mass spectrometers can measure isotope ratios to parts per thousand, sometimes better. Laser ablation can map elements across grains, revealing microscale histories. These tools turn rocks into datasets, and datasets into tests. But tools do not replace judgment, they sharpen it. Then we look for co-occurring markers in the same stratigraphic interval. Fly ash morphologies, unusual polymers or their residues, and synchronized metal spikes. We look for spheroidal particles with combustion chemistry, not volcanic glass. We look for nitrogen signals consistent with industrial fixation, not just changing ecology. We look for metals rising together in proportions that match mining and smelting. The interval must be a cluster of anomalies, not a lone outlier. We also compare marine and continental records for the same time slice. A true global technosignature should appear in multiple depositional environments. If the signal is atmospheric, it should land in oceans and lakes alike. If it is river-driven, it should appear downstream in deltas and shelves. Cross-environment correlation is difficult, but it is powerful. It is one way to separate global forcing from local quirks. We prioritize anomalies that are stratigraphically sharp and globally synchronous. Slow trends are easier for nature to create and harder to attribute. A sharp boundary suggests a rapid driver, whether volcanic, impact, or industrial. Synchronous layers suggest atmospheric distribution or global ocean chemistry. In stratigraphy, time is encoded as thickness, and thickness can lie. So we use dating, correlation, and multiple proxies to constrain the clock. We also look for spatial patterns that imply infrastructure. Localized halos around potential sites paired with broader atmospheric signals would be suggestive. A city might leave a concentrated rubble lens and a metal halo in nearby sediments. A power plant might leave fly ash locally, plus a faint global background. A reactor might leave a tight isotopic anomaly, plus corrosion products and concrete traces. The pattern would be nested, local intensity within global haze. Now the tension tightens because calibration turns back on us. If humans disappeared, our deep time visibility might be weaker than our intuition suggests. We feel loud because we live inside the noise we make, but geology averages, mixes, and erases. It cares about what is preserved, not what was dramatic. The planet is not obligated to remember us clearly. Our loudest signals are short-lived in the rock record. Plastics degrade, radionuclides decay, and cities become chemically ordinary rubble. Steel becomes iron oxides, then becomes part of sediment. Glass devitrifies, then becomes silica-rich fragments. Concrete becomes carbonate and clay mixtures. The distinctive becomes mundane, and the mundane becomes background. Even our carbon spike can be blurred by later carbon cycle recovery and burial. Over long spans, Earth rebalances and the anomaly becomes one excursion among many. Weathering draws down CO2, oceans absorb and redistribute carbon, and sediments bury it. The system has feedbacks that damp extremes, though not on human timescales. In 10 million years, the atmosphere might look ordinary again. The rock record would still hold a scar, but it might be faint. So the absence of evidence for earlier civilizations may tell us little. The planet's archive is sparse, and our sampling is thinner still. Most rocks are buried, subducted, or never deposited in continuous sequences. We drill tiny holes in a vast crust and call it a survey. What if the evidence exists, but we have not cored the right basin? What if the key layer is in a subducted margin, now melted into magma? That is the epistemic edge of the Great Filter. A civilization can be filtered out, and its evidence can be filtered out afterward. Extinction is one filter, but erosion is another. Even survival is not guaranteed to be legible. We might be searching for a signature that is real but not durable. The universe might be full of brief sparks that leave little ash. Yet the Great Filter still looms, because our own signatures are being written now. The same proxies we seek in ancient rock are forming under our feet. Every ton of CO2 shifts isotopes, every fertilizer plume shifts nitrogen, and every combustion particle settles somewhere. We are creating a layer that future stratigraphers could name. The question is whether they could interpret it correctly. Would they see a civilization, or only a strange event? If we want to know whether we are first, we must accept how close proof sits to the limits of preservation. Mystery survives not because answers are impossible, but because evidence is fragile. The planet is a palimpsest, scraped and rewritten by tectonics and time. Some ink soaks deep, and some washes away. Our task is to learn which is which. Now we pivot toward the central question again, with stricter boundaries. We cannot claim certainty from a single proxy, and we cannot dismiss the question from silence. The discipline here is methodological, not emotional. We must define what would count as detection and what would count as coincidence. We must also define what would count as refutation if the layer is absent. Otherwise, the search becomes a mirror for our hopes. Oklo remains the anchor because it shows both preservation and deception. It preserved a nuclear story for 2 billion years, and it also shows nature can mimic design. Oklo's story survived because conditions were right, water, ore, and mineral traps aligned. But it also survived in a way that could mislead a careless interpreter. That double lesson is exactly what we need. It is a calibration point for skepticism. So we end with what the evidence allows, what it forbids, and what it warns. Earth is a palimpsest, and our chapter is being etched into it fast. The evidence allows multi-proxy anomalies to be preserved, at least in stable basins and cratons. It forbids easy conclusions from single spikes, because nature has its own repertoire of shocks. It warns that our confidence should scale with convergence, not with drama, and it warns that even our own era may become ambiguous with enough time. After all the clues, we return to the central question, not to declare a lost civilization, but to define what detection would require. Then we step into the final chapter, where the Great Filter stops being abstract and becomes a choice. We end where we began, in Gabon, with a reactor that never needed hands. Oklo is extraordinary because it is real, measured, and internally consistent across decades of scrutiny. Oklo is also natural, built from uranium, water, geometry, and time, then sealed inside rock like a slow, patient experiment. Picture the outcrops in the equatorial light, where laterite soils glow red and the forest presses close. Beneath that surface, ancient sandstones and clays hold ore bodies like dark seams. In the lab, those seams become powders, spectra, and ratios, numbers that refuse to be romantic yet still feel uncanny. That matters because it resets our instincts about evidence, especially when we look for intention. Nature can imitate technology when physics allows the same outcomes, and it does so without motive or design. Technology can also become geology when time grinds structure into chemistry, until even a machine signature looks like ordinary mineralogy. Oklo is the double lesson, preservation and deception in one site, balanced on a knife edge of conditions. Water had to percolate through the ore as a neutron moderator, slowing neutrons so fission could sustain itself. The uranium had to be concentrated enough, and the geometry had to keep neutrons from escaping too quickly. Even the reactor's rhythm was physical. As water heated and boiled away, moderation dropped, the chain reaction slowed, and the system cooled back into readiness. The central question stays sharp because it is not really about Oklo at all. Are humans Earth's first technological intelligence, or only the latest attempt? If earlier civilizations rose, could Earth have erased them into silence, leaving only ambiguous chemistry behind? If none rose, what does that imply about rarity and filters, and about how fragile the path to industry might be? Oklo teaches humility in two directions, and neither is comfortable. It warns us not to overread anomalies as intention, because the planet can generate patterns that look engineered. It also warns us not to assume absence means nothing happened, because erosion, burial, and heat can erase even large stories. Now we weigh what is confirmed, because the story needs a flaw. Oklo's depleted uranium-235 is confirmed across samples and labs, and the depletion is not subtle. The isotopic ratios shift away from what modern uranium should look like, as if someone had already burned part of the fuel. That burn has a fingerprint. Fission product neodymium yields and trapped xenon isotopes match reactor physics, including the distinctive mix expected from sustained chain reactions. The enabling condition is also plain, once you remember radioactive half-lives. 2 billion years ago, uranium-235 was more abundant relative to uranium-238, because U-235 decays faster. The arithmetic is simple, but the implication is strange. Earth once carried a more reactive fuel supply by default. Oklo did not need invention, it needed the right era. We also know Earth has reset itself repeatedly without any help from mines. Plate tectonics recycles ocean crust on roughly 200 million-year clocks, and it does so relentlessly. Whole basins are created, filled, and then swallowed, taking their sediments and any artifacts with them. On land, sedimentation buries, compacts, and alters, then metamorphism recrystallizes and diffuses, turning crisp boundaries into smeared gradients. Erosion and groundwater keep editing even stable continents, and the edits are not gentle. Rivers cut down through layers like slow saws, and glaciers can plane landscapes into new beginnings. Groundwater moves ions through pore spaces, dissolving some minerals and precipitating others, rewriting a rock's chemistry long after it formed. The longer the time span, the more chances there are for the archive to be rearranged. Extinction mechanisms are also not speculative, and their signatures are among the clearest timestamps we have. Impacts leave iridium, shocked minerals, and boundary layers with global reach, sometimes with tiny spherules that cooled from vaporized rock. Flood basalts leave mercury spikes, ash, and carbon cycle disruption tied to warming and anoxia, and they can persist for hundreds of thousands of years. Multi-stressor stacking can collapse ecosystems fast, then delay recovery for millions of years, as food webs rebuild from simplified survivors. Oxygenation history is another hard anchor, and it is written into multiple independent lines of evidence. The Great Oxidation Event is recorded in sulfur mass-independent fractionation collapse, a signal that disappears when atmospheric chemistry changes. It is recorded in banded iron formations and continental red beds, where iron flips between soluble and insoluble states as oxygen rises. Oxygen was both toxin and tool, poisoning many anaerobes while enabling higher energy metabolisms that made larger bodies feasible. Those anchors set constraints on any prior advanced civilization claim, and the constraints are physical, not philosophical. Deep time preservation is poor, especially for surface artifacts and ocean floor infrastructure, because those are the first things Earth recycles. The best archives are stable cratons and protected sedimentary basins, where layers can sit quietly for immense spans. Even there, later heating, pressure, and migrating fluids can blur the ledger, turning sharp industrial signals into ambiguous background. So we synthesize what a robust technosignature would require if we are being strict with ourselves. It would need to be global, or at least widely dispersed beyond local geology, because local oddities are easy to misread. It would need multiple independent proxies that converge in the same time slice, so no single measurement carries the whole claim. It would need a timestamp that survives diagenesis and later overprints, because the rock record is rarely pristine. A single spike is not enough, because nature makes spikes, and it makes them often. Carbon isotope excursions can be volcanism, methane release, or productivity shifts, and the same curve can come from different causes. Metal enrichments can be hydrothermal, redox-driven, or sediment-focusing concentrating elements without any industry at all. Even fission-like patterns can be natural, and Oklo proves it. An apparent technological signature can emerge from chemistry plus chance. A strong case would look like a coupled suite, where several lines of evidence lock together. Carbon shifts aligned with combustion particles and coordinated heavy metal patterns would be harder to dismiss as coincidence. Nitrogen cycle disruption that matches industrial fixation rather than ecology alone would add another independent axis of constraint. Possibly unusual halogen chemistry or persistent synthetic residues, if any survive, could act like molecular fossils. Rare, but diagnostic when found. It would also need context that resists alternative stories, because the first job is always to rule out the ordinary. The layer would have to appear across marine and continental settings, not just in one basin with unusual circulation. It would have to align with rapid environmental change and not drift randomly through time. It would have to survive aggressive tests for volcanism, impact, and diagenetic alteration, including the possibility that later fluids move the very elements we are measuring. So what do we have right now when we apply those rules with discipline? We have no confirmed global multi-proxy technosignature for pre-human industry, and that absence is meaningful. We have intriguing anomalies in Earth history, but they remain explainable by known natural mechanisms, especially when you allow for incomplete sampling. The conservative reading is simple, and it is not satisfying because it leaves the mystery intact. That conservative reading is not a declaration of impossibility, and it should not be used as one. It is a statement about evidence quality and preservation bias, which are not the same as truth. Billion-year timescales leave wide uncertainty, especially for subtle or low-energy civilizations that never reshaped the planet. A society that stayed small, recycled tightly, or avoided global dispersal could be nearly invisible, leaving only faint chemical nudges that look like noise. We also have uncertainty because our sampling is thin, and the thinness is easy to forget. We drill and core tiny fractions of the crust, then generalize from what we happen to recover. We lose most seafloor history to subduction, so the largest surface on Earth is also the least archived. We rely on the basins that happen to survive and the outcrops we happen to find, which is a kind of geological survivorship bias. So the answer hidden in the stone is conditional, and that conditionality is the honest ending. If a prior civilization was large, energetic, and long-lived, we should expect some durable global fingerprint, even after erosion and tectonics. None is currently confirmed, which pushes probability toward humans being first, at least in the industrial sense. If a prior civilization was brief or subtle, the archive may not convict it, and the silence may be an artifact of how Earth keeps records. Now we reframe the Great Filter with Earth's own timeline. Earth does not show one clean gate that opens and stays open, like a door that finally clicks. It shows narrow corridors, long plateaus, and repeated near resets, where progress is possible but never guaranteed. The filter may be a sequence, not a single wall, several hard steps separated by long waits and occasional catastrophes. Oxygenation was one corridor because it killed and enabled at once, and it did so on a planetary scale. Eukaryotes and multicellularity took long delays that hint at difficulty, as if complexity needed rare alignments of energy and ecology. Mass extinctions repeatedly pruned complexity and reshaped trajectories, clearing niches while also erasing experiments that might have gone further. Intelligence, then industry, arrived extremely late in the record, close to the present edge of deep time. That sequence changes how we interpret the cosmic silence, because it suggests many ways to fail. Maybe the hardest steps are behind us, and few worlds ever reach technology, so the sky stays quiet. Maybe the hardest step is ahead, and many worlds self-terminate quickly, leaving only brief flashes. Maybe both are true, and the silence is a compounded probability, small odds multiplied again and again. Earth's history also shows that survival is not only about intelligence, and that is the uncomfortable part. It is about stability, feedback control, and cooperation under stress. Because complex systems fail in complex ways, the planet has thrown impacts, volcanism, climate swings, and redox crises at life, and each one tests resilience differently. Many lineages endured, but endurance was never guaranteed, and dominance was never permanent. So we personalize the stakes without turning it into a sermon, because the physics is already serious enough. If the Great Filter is ahead, our choices matter in a literal physical sense, not as metaphor. Energy use, biosphere disruption, and conflict scale into planetary forcing, and the atmosphere records those choices in ratios and residues. The future can become a boundary layer, thin and unmistakable, the kind of line a distant geochemist would recognize. If the great filter is mostly behind us, the stakes still rise, just in a different direction. Rarity would mean we are an uncommon outcome in a vast experiment, a statistical fluke with responsibilities attached. Responsibility scales with rarity, because there may be fewer second chances elsewhere, and fewer parallel successes to learn from. Being first would not be a victory. It would be a duty, carried forward without applause. Oklo returns as the quiet footnote that keeps the tone grounded, because it refuses both fantasy and complacency. A natural reactor ran, cycled and shut down, then waited 2 billion years for discovery, its products locked in mineral cages. It is not a message, but it is a reminder that physics can do strange things when conditions align. It is also a reminder that rocks keep receipts, even when stories are lost, and even when the handwriting is hard to read. So we end with what we can honestly say, and honesty here is a kind of discipline. We have no robust proof of an earlier technological civilization on Earth, at least none that survives the standards we would demand in any other science. We have strong reasons why proof would be hard to preserve and hard to interpret, especially across deep time and active geology. We have a planet that erases and a physics that records, and we live between them, searching for signals that might never have been durable. The haunting image is not a ruined city under the sea lit by divers and nostalgia. It is an archive with missing pages where the gaps are part of the message and the silence has structure. Oklo sits in Africa like a marginal note from deep time, small in area yet enormous in implication. The future is the next layer of rock, and we are writing it now, grain by grain, molecule by molecule, while the planet quietly prepares to file it away. We began with an impossible-looking fact, a nuclear reactor in Gabon that ran 2 billion years ago without hands, plans or intent. From Oklo's isotopic scars we learned a harder lesson. Earth can preserve a signal for eons, and still make nature look engineered. Then the deeper pattern emerged. The planet's history is a palimpsest. Plates subduct, sediments bury, heat recrystallizes, oceans corrode, and time edits almost everything we would call proof. That shredder forces a different hunt, not for ruins, but for bookkeeping errors in carbon, nitrogen, metals, radionuclides, soot, plastics turned to unfamiliar organics, and the synchronized fingerprints of industry. Yet Oklo also warns that geology counterfeits, so any claim must survive redundancy, multi-isotope bundles, mineral context, global replication, and tests designed to fail. We traced how collapse can be loud even when artifacts are quiet, with extinctions written in thin boundary seams, and with rates that betray stacked stresses. We watched the oxygen catastrophe rewrite the rules of survival, turning a microbial innovation into a mass die-off, and revealing that filters can be planetary, not just cosmic. And when we widened the lens to the silent galaxy, the great filter stopped being an abstract idea and became a question about fragility. Detectable civilizations may be brief, and deep time may hide both their rise and their end. So the threads converge on a practical frontier, build a field-ready protocol, target cratons and long-lived basins, seek convergent proxy suites, and define what would count as detection and what would count as absence. So are we Earth's first technological intelligence, or the latest survivors of a filter that erased the others clean? The honest answer is that the rocks do not yet convict a predecessor, but they also cannot promise one never existed, because Earth can both forge false machines and grind real ones into ordinary stone. Oklo is the planet's quiet reminder that the boundary between accident and intention can blur, while the boundary between survival and disappearance can be razor thin. Whether we are first or merely last, the next layer in the record is being written now, and it will testify less to our power than to our restraint. If you want to know what came before and what might come after, support the measurements, open data, deeper cores, cleaner baselines, and the humility to let the evidence say, not yet.